So, here's something worth thinking about as you settle in tonight. Right now, as you're lying there, something is holding you down. You can feel it in the weight of your own body pressing into the mattress, in the way your arms settle at your sides, in the gentle pull on your eyelids. That something has been with you every moment of your life. You've never escaped it, not for a single second. And neither has anything else in the observable universe. Every grain of sand, every drop of water, every star in every galaxy, all of it obeys the same invisible authority, has obeyed it since the first instant after the Big Bang, and will go on obeying it long after our sun burns out and goes cold. We call it gravity. And you'd think after 400 years of modern science, after Newton and Einstein and particle accelerators and space telescopes and detectors that can measure a shift smaller than 1,000th of the width of a proton, you'd think we'd know what it is by now. We don't. We can describe what it does with extraordinary precision. We can predict its effects to 14 decimal places. We can use it to send spacecraft to the outer planets, to detect the collision of black holes a billion light years away, to correct the clocks on GPS satellites so your phone knows which street you're on. But if you ask a physicist, any physicist, the most brilliant mind working today, what is gravity actually? You will watch something interesting happen. They will pause. They will choose their words very carefully, and what they will tell you, if they're being honest, is that nobody really knows. Here's what makes that extraordinary. Gravity was the first force humans ever noticed. Long before anyone understood magnetism or electricity, long before anyone dreamed of nuclear forces holding atoms together, gravity was right there, obvious, inescapable, pulling apples from trees and keeping feet on the ground. It is the most familiar phenomenon in all of physics, and it remains today, in the 21st century, the most mysterious. And here's where it gets stranger. For 300 years, we called gravity a force, a pulling force, reaching across empty space, tugging every object toward every other object. Newton gave us a formula that made this idea so precise, so powerful, that it predicted the existence of planets no one had ever seen. That formula worked so well that people stopped asking what gravity actually was. The formula was enough. Then Einstein came along and said, actually, gravity isn't a force at all. There is no pulling. There is no reaching across space. What we experience as gravity is something completely different. Something that would have sounded like madness to Newton and like pure nonsense to Aristotle. Einstein said that massive objects bend the very fabric of space and time, and that everything, including you, including light, simply follows the curves in that fabric. You're not being pulled down right now. The Earth beneath you is curving space-time, and your body is following that curvature. You feel the mattress pushing up against you, and your brain interprets that as weight, as gravity pulling you down. But there is no pull. There is only geometry. And now, in our own time, even Einstein's beautiful picture is showing cracks. Because when physicists try to apply the rules of quantum mechanics, the rules that govern atoms and particles and everything very small, to Einstein's curved space-time, the mathematics breaks. It produces infinities. It contradicts itself. The two greatest theories in physics, quantum mechanics and general relativity, each spectacularly successful on its own, refuse to work together. And gravity is the place where they collide. So, tonight, I want to walk you through something. Slowly, carefully, with no rush at all. I want to tell you the story of how humans have tried, across 25 centuries, to understand the most obvious and most baffling thing in the universe. And what I think you'll find as we go is that the story has a peculiar shape. Because every time someone figured out what gravity is, every time a brilliant mind peeled away one explanation and revealed a deeper truth underneath, what they found was not an answer. What they found was a better question. Aristotle said gravity was a property of matter itself, an inner tendency, a longing for home. That was the first mask. It lasted 2,000 years. Newton tore that mask away and said gravity was a force, a real, measurable, mathematically precise force acting between bodies across empty space. That was the second mask. It lasted 228 years. Einstein tore that mask away and said gravity was geometry, the curvature of space-time itself, shaped by mass and energy. That was the third mask. It has lasted 110 years so far, and it is beginning to tear. Underneath it, physicists suspect there is something else. A fourth mask, perhaps the last one, perhaps not. Gravitons, strings, loops, extra dimensions. Ideas so strange that the people proposing them are the first to admit they can't yet prove them. What is gravity? What is the thing that holds you to this bed, that holds the moon in its orbit, that collapses dying stars into objects so dense that time itself stops at their edges? How did we go from thinking gravity was obvious to realizing it might be the deepest mystery in all of physics? And is there a chance, even a small one, that the force you feel right now, the weight pressing you into the mattress, is leaking into our universe from somewhere else entirely, from a dimension you will never see or touch? That's where we're going tonight. So, let yourself settle in, let the day fall away. We have a long, strange, beautiful road ahead of us, and it starts where almost everything in Western science starts, with a man in a toga in ancient Athens, watching a stone fall to the ground and asking a question that sounded so simple, he thought he already knew the answer. Let's go back, way back, 2,300 years, give or take. The Mediterranean world in the 4th century before the Common Era was a world of city-states and empires, of olive groves and marble temples, of philosophers arguing in shaded courtyards while slaves carried water from public fountains. Athens was past its political peak by this time, its great age of Pericles and the Parthenon already fading into memory. But intellectually, philosophically, it was at the height of its power. And at the center of Athenian intellectual life stood a man named Aristotle. Aristotle was born in 384 BCE in Stagira, a small town in the northern reaches of the Greek world in what is now the Chalkidiki Peninsula. His father, Nicomachus, was the personal physician to King Amyntas of Macedon, which gave the young Aristotle a connection to royalty that would shape his entire life. When he was about 17, he traveled to Athens and enrolled in Plato's Academy, the most prestigious school of philosophy in the ancient world. He stayed for nearly 20 years, first as a student, then as a teacher, absorbing Plato's ideas and gradually, carefully, beginning to disagree with them. After Plato's death, Aristotle left Athens, spent some years traveling, and eventually accepted an extraordinary invitation. King Philip of Macedon asked him to come north and tutor his son, a restless, ambitious 13-year-old boy named Alexander. Yes, that Alexander, the one who would conquer most of the known world before he turned 30. Aristotle taught Alexander for about 3 years, introducing him to Homer, to medicine, to philosophy, to the natural sciences. What Alexander took from those lessons is hard to say. He burned cities and built an empire. But Aristotle took something too, a lifelong habit of careful observation and classification that he would apply to everything from the organs of squid to the motion of falling stones. When Aristotle returned to Athens, he founded his own school, the Lyceum, and began producing a body of work so vast, so comprehensive, so systematically organized, that it would dominate Western thought for nearly 2 millennia. He wrote about logic, ethics, politics, poetry, biology, metaphysics, and, crucially for our story, about physics. His book on the subject is called, with characteristic directness, Physics. And in it, he laid out an explanation for why things fall that was so intuitive, so satisfying, so perfectly aligned with everyday experience that virtually no one questioned it for over 2,000 years. Here is what Aristotle believed. He believed that the universe was made of 5 elements. 4 of them were earthly: earth, water, air, and fire. The 5th, called ether, made up the heavens, the stars and planets and celestial spheres. Each earthly element had a natural place in the cosmos. Earth, the heaviest, belonged at the center. Water belonged just above earth, air above water, fire above air. And each element, when displaced from its natural place, would strive to return to it. This was Aristotle's explanation for gravity. A stone falls because it is made mostly of the element earth, and Earth's natural place is at the center of the universe, which, in Aristotle's model, was the center of the Earth. The stone isn't being pulled. Nothing is reaching out and grabbing it. The stone is going home. It has an inner tendency, almost a desire, to reach its proper place in the cosmic order. Smoke rises for the same reason, but in reverse. Smoke is made mostly of fire and air, and those elements naturally move upward, away from the center. Think about how elegant that is. It explains why heavy things fall down. It explains why fire goes up. It explains why water flows downhill and pools in low places. It explains why the Earth itself sits at the center of everything, because Earth is the heaviest element, and the heaviest element naturally congregates at the lowest point, the center. And it does all of this without invoking any invisible force, any mysterious action at a distance, any mechanism that you can't directly see. The stone falls because of what the stone is. Gravity, in Aristotle's picture, isn't something that happens to objects. It's something that lives inside them. Now, Aristotle went further. He also believed that heavier objects fall faster than lighter ones. That seemed perfectly obvious. You drop a boulder and a pebble side by side, and the boulder hits the ground first. You drop a feather and a coin, and the coin wins easily. Aristotle generalized this into a principle. The speed of a falling object is proportional to its weight. Twice as heavy, twice as fast. 10 times as heavy, 10 times as fast. He also believed that a vacuum was impossible. If you removed all the air from a space, he argued, objects would fall infinitely fast through it, which is absurd. Therefore, a vacuum cannot exist. Nature, as the later saying went, abhors a vacuum. And he believed that the heavens operated under completely different rules than the Earth. Down here, in the sublunary realm, things were messy. Objects fell, things burned, water evaporated, matter changed. But up there, beyond the moon, everything was perfect. Celestial objects moved in perfect circles, eternally, without friction or decay, carried by crystalline spheres. The heavens were made of ether, which was eternal, unchanging, divine. The physics of Earth and the physics of the sky were fundamentally, categorically different. Take all of that together, the natural places, the inner tendencies, the proportionality of weight and speed, the impossibility of vacuum, the division between earthly and heavenly physics. What you get is a complete picture of why things fall, where they fall, and how fast they fall. It answers every question a curious person might ask about the everyday experience of gravity. It does so with internal consistency, and with reference to ideas that feel true to common sense. And it comes wrapped in the authority of a man widely regarded as the most brilliant thinker of his age, a man whose former student had conquered the world. No wonder it lasted so long. Aristotle's explanation had everything a good explanation needs. It matched daily experience. It was logically coherent within its own framework. It connected to a broader worldview about the structure of the cosmos. And it came from the most authoritative source in the ancient world. When you have all 4 of those things working in your favor, you can survive almost any amount of contrary evidence. Because the contrary evidence looks like noise, and the theory looks like truth. And there's a deeper reason too, one worth sitting with. Aristotle's gravity was comforting. In his universe, everything had a place. Stones belonged at the center, fire belonged at the top, the stars moved in perfect circles on crystalline spheres. There was an order to things, a hierarchy, a structure that was not just physical but moral and aesthetic. The universe was designed, it was beautiful, it made sense. Humans, living on the surface of the Earth, occupied a natural station in a comprehensible cosmos. That is a deeply satisfying picture of reality. People don't give up deeply satisfying pictures easily. For roughly 2,000 years, from the 4th century BCE through the 16th century CE, Aristotle's picture of gravity was essentially unchallenged in the Western world. The Roman Empire adopted Greek learning, but added little to it in the way of fundamental physics. When Rome fell and Europe entered the medieval period, Aristotle's works were preserved and transmitted through the Islamic world, where scholars in Baghdad, Cairo, and Cordoba translated them into Arabic, studied them, commented on them, and in many cases improved on them. When those texts returned to Europe in the 12th and 13th centuries, translated from Arabic into Latin, they became the foundation of university education. Thomas Aquinas, the great medieval theologian, built much of his philosophical system on Aristotelian foundations. The Catholic Church eventually adopted Aristotle's physics as part of its official worldview. Questioning Aristotle became, in some contexts, dangerously close to questioning God. But there were cracks, and to find them, we need to look beyond Europe, to the East, where the most important scientific work in the world was happening for centuries, while European scholars were largely copying old manuscripts and arguing about theology. The Islamic Golden Age, roughly the 8th through the 14th centuries, was one of the most intellectually productive periods in human history. The Abbasid caliphs in Baghdad had sponsored translation movements on a massive scale, hiring scholars to render Greek, Persian, Indian, and Syriac texts into Arabic. There was an institution in Baghdad called the House of Wisdom, Bait al-Hikmah, where scholars gathered, translated, debated, and pushed the boundaries of knowledge in mathematics, astronomy, medicine, and what we would now call physics. This was not a culture that simply preserved Greek ideas in amber. This was a culture that was doing new science. Al-Khwarizmi invented algebra. The word algorithm comes from the Latinized form of his name. Al-Biruni calculated the radius of the Earth to within about 9 miles of the modern value. And a man named Ibn al-Haytham, born in Basra around 965 CE, did something that arguably mattered more for the future of physics than anything else that happened between Archimedes and Galileo. Ibn al-Haytham wrote a masterwork called the Kitab al-Manazir, the Book of Optics, during a period of house arrest in Cairo, and in it he laid down something extraordinary, the systematic experimental method. He didn't just argue about how light worked. He built dark chambers, early versions of the camera obscura, and tested hypotheses with controlled experiments. He measured angles, he varied conditions, he recorded results. He wrote that the seeker of truth should not trust the writings of the ancients, but should instead submit claims to argument and demonstration. That is the scientific method, articulated 600 years before Newton. And within this vibrant tradition, scholars noticed problems with Aristotle's physics. Even within the Islamic tradition, scholars noticed problems. The Persian polymath Ibn Sina, known in the West as Avicenna, wondered in the 11th century why a thrown ball keeps moving after it leaves the hand. Aristotle had said the air pushes it forward, rushing in behind the ball to fill the vacuum it would otherwise leave. But that explanation never sat right with everyone. The air should resist the ball's motion, not sustain it. And in the 14th century, the French philosopher Jean Buridan proposed a different idea. He said that when you throw a ball, you impart to it something he called impetus, a kind of internal quantity of motion that keeps it going. The ball doesn't need the air to push it. It carries the impetus within itself, and it keeps moving until friction and air resistance gradually drain that impetus away. Buridan's impetus theory was a significant step toward what Newton would later call inertia. But Buridan still worked within the Aristotelian framework. He wasn't overthrowing Aristotle, he was patching him. And the big ideas, the natural places, the division between earthly and heavenly physics, the proportionality of weight and speed, those remained in place, unquestioned, seemingly unquestionable. The first person to seriously and systematically challenge those ideas, to actually go out and test them, rather than simply argue about them from a chair, was a man born in Pisa in 1564, a man with a talent for making enemies nearly as impressive as his talent for making discoveries. His name was Galileo Galilei, and what he did to Aristotle's picture of gravity would set the stage for everything that followed. But before we get to Galileo, I want you to sit with something for a moment. For 2,000 years, the answer to "why do things fall" was "because they're going home." The stone falls because it is made of earth, and earth belongs at the center. That answer felt right. It matched what people saw every day, and it came with the seal of the greatest philosopher in history. 2,000 years. Roughly 80 generations of human beings lived and died believing that gravity was an inner longing of matter for its natural place. Not because they were stupid, not because they lacked curiosity, but because the answer was so satisfying, so complete, so seemingly obvious that nobody thought to question it. And that, as it turns out, is the most dangerous kind of answer in all of science. The kind that feels so right that you stop looking. Galileo looked. Galileo Galilei was born on February 15, 1564, in Pisa, in the Duchy of Florence. His father, Vincenzo Galilei, was a musician and music theorist, a man who made his living by lutes, but earned his intellectual reputation by challenging received authority in musical theory. He ran experiments on strings and sound, testing the claims of ancient writers against actual measurements, and found that the ancients were often wrong. The son would inherit both the method and the temperament. Young Galileo was sent to the University of Pisa to study medicine, a respectable and potentially lucrative career. But he was drawn, almost against his will, to mathematics. The story goes that he happened to attend a geometry lecture and was so captivated that he abandoned medicine and devoted himself to mathematics and natural philosophy, to his father's considerable frustration. Vincenzo had hoped for a doctor, not another impoverished scholar. But Galileo had found his calling, and he was not a man who could be easily redirected. By his mid-20s, Galileo was teaching mathematics at the University of Pisa, and he was already developing a reputation for being argumentative, brilliant, and almost impossibly difficult to work with. He questioned things. He challenged established professors in public. He did something that almost no one in the academic world of the late 16th century did regularly. He conducted experiments. And one of the first things he experimented with was falling. Aristotle had said that heavier objects fall faster than lighter ones. A 10-pound stone should fall 10 times faster than a 1-pound stone. This was taught in every university in Europe as established truth. Galileo decided to actually check. The famous story, probably embellished over the centuries but rooted in something real, places Galileo at the top of the Leaning Tower of Pisa, dropping 2 balls of different weights simultaneously and watching them hit the ground at the same time. Whether or not this particular demonstration happened exactly as described, Galileo certainly performed careful experiments with falling objects, rolling balls down inclined planes to slow the motion enough to measure it precisely. And what he found contradicted Aristotle completely. Heavy objects and light objects fall at the same rate. A cannonball and a musket ball released together hit the ground together. The difference you see in everyday life, a feather floating while a rock thuds, is due to air resistance, not to any fundamental difference in how gravity treats them. In a vacuum, a feather and a cannonball would fall side by side, accelerating at exactly the same pace, hitting the ground at exactly the same instant. Think about what that means. Aristotle had said that gravity is proportional to weight, that the heavier the object, the faster it falls, because heavier objects have more of the element earth in them, and more earth means a stronger tendency to seek the center. Galileo's experiments demolished that idea. Gravity doesn't care how heavy something is. A grain of sand and a boulder accelerate at the same rate. Whatever gravity is, it treats all matter equally, regardless of quantity. That is a very strange property for a force that is supposedly about the inner nature of specific materials. But Galileo went further. He didn't just show that Aristotle was wrong about the relationship between weight and speed. He discovered the actual mathematical law that governs falling. By rolling polished bronze balls down carefully constructed inclined planes and timing their descent with a water clock, measuring how much water flowed through a thin tube during each interval, he established that falling objects accelerate uniformly. Their speed increases by the same amount during each equal interval of time. In each successive second, a falling object covers more distance than it did in the second before, and the increase follows a precise mathematical pattern. The distance covered is proportional to the square of the time elapsed. This was revolutionary. For the first time in history, someone had described the behavior of falling objects with a mathematical equation derived from actual measurement rather than philosophical reasoning. Galileo wasn't asking why things fall. He wasn't proposing any new theory of gravity to replace Aristotle's natural places. He was simply describing how things fall, with precision, with mathematics, with reproducible numbers. And that shift, from asking why to asking how, from seeking cosmic purpose to seeking mathematical law, was one of the most important intellectual transitions in human history. Galileo also made another observation that would prove crucial, though its full significance wouldn't become clear until Newton. He studied projectile motion, the arc traced by a cannonball or a thrown ball, and he realized that the horizontal and vertical components of that motion are independent of each other. The horizontal part proceeds at a constant speed, unaffected by gravity. The vertical part accelerates downward, governed by the same uniform acceleration he had measured on his inclined planes. The combination produces a parabola, a smooth mathematical curve. Motion could be decomposed into components. Those components could be analyzed separately, and the analysis was mathematical. But Galileo's work on falling bodies and projectile motion was only part of his assault on the Aristotelian universe. In 1609, he heard that a Dutch spectacle maker had built a device that made distant objects appear closer. Galileo immediately grasped the principle, built his own version, improved it dramatically, and pointed it at the sky. What he saw destroyed the last pillars of Aristotle's cosmology. The moon was not a perfect, smooth sphere of celestial ether. It had mountains and craters and valleys, a landscape as rough and irregular as the Earth's. Jupiter had 4 moons orbiting around it, proof that not everything in the heavens revolved around the Earth. Venus showed phases, waxing and waning like our moon, which only made sense if Venus orbited the Sun, not the Earth. The Milky Way, that hazy band of light across the sky, was made up of countless individual stars, too faint to see with the naked eye, suggesting a universe far larger and more populated than anyone had imagined. Each observation drove another nail into the coffin of the Aristotelian cosmos. The heavens were not perfect. Not everything orbited the Earth. The universe was not a cozy, finite, neatly ordered place with the Earth at its center. It was vast, messy, and governed by rules that Aristotle had never dreamed of. The Catholic Church, which had adopted the Aristotelian, earth-centered universe as official doctrine, was not pleased. In 1616, the Church declared the Copernican model, in which the Earth orbits the Sun, to be formally heretical. In 1633, Galileo was tried by the Inquisition, forced to recant his support for the Copernican system, and sentenced to house arrest for the remainder of his life. He spent his final years, nearly blind, still working, still thinking, still fighting, in a villa outside Florence, where he died in January of 1642. Almost exactly a year later, in a farmhouse in Lincolnshire, Isaac Newton was born. The timing is worth pausing on. The old world and the new world, ending and beginning within months of each other. Meanwhile, 1,000 miles to the north, another man was quietly doing something equally revolutionary, though his work would only reach its full power when combined with Galileo's. His name was Johannes Kepler, and his obsession was not falling stones, but orbiting planets. Kepler was born in 1571 in the small town of Weil der Stadt in the Duchy of Württemberg, in what is now southern Germany. His childhood was harsh. His father was a mercenary soldier who abandoned the family when Kepler was young. His mother was later accused of witchcraft, and Kepler spent years defending her against the charges. He was sickly, awkward, deeply religious, and possessed of a mathematical intuition that bordered on mystical. He believed with absolute conviction that God had constructed the universe according to mathematical principles, and that it was humanity's sacred duty to discover those principles. Kepler studied at the University of Tübingen, where he encountered the Copernican model of the solar system, the radical idea that the Earth was not the center of the universe, that the Sun occupied the center and the planets, including Earth, orbited around it. Copernicus had published this theory in 1543, the year he died, and it had been gradually gaining adherents despite fierce opposition from both the Catholic Church and many Protestant authorities. Kepler became a devoted Copernican, convinced that the sun-centered model was not just mathematically convenient, but physically true. In 1600, Kepler traveled to Prague to work with Tycho Brahe, the great Danish astronomer, who had spent decades making the most precise naked-eye observations of planetary positions in history. Tycho was a remarkable figure, a nobleman with a golden prosthetic nose, replacing the one he'd lost in a duel, who had built an observatory on an island and filled it with the finest instruments money could buy. He was a meticulous observer, but not a great theorist. Kepler was an indifferent observer, but a mathematical genius. Their collaboration was tense, brief, and astonishingly productive. When Tycho died unexpectedly in 1601, Kepler inherited his observational data, particularly his exquisitely precise measurements of the orbit of Mars, and he set to work trying to find the mathematical law that governed the planet's motion. It took him years. Kepler worked with a doggedness that bordered on mania. He tried over 70 different combinations of circular orbits, of circles within circles, of equant points and eccentric centers, all the traditional geometrical devices that astronomers had used since Ptolemy. None of them worked. Mars stubbornly refused to follow a circular path. The discrepancies were small, just 8 minutes of arc, a tiny fraction of a degree, but Kepler trusted Tycho's data, and those 8 minutes of arc demanded an explanation. Eventually, after exhausting every possible circular model, Kepler tried something nobody had tried before. He abandoned the circle entirely and tested whether Mars might follow an elliptical orbit, an oval-shaped path with the Sun at one focus rather than at the center. The ellipse fit perfectly. Every single observation matched, the deviation vanished. Kepler later wrote about the experience in characteristically passionate language, comparing his years of struggle to a war against Mars, the planet and the god of war alike, and his discovery of the ellipse to finally conquering a stubborn enemy through a flanking maneuver that he himself hadn't anticipated. He had gone into the battle expecting circles. The universe gave him ellipses. And in accepting what the universe offered, Rather than insisting on what he expected, Kepler showed a kind of intellectual humility that science would need again and again in the centuries to come. This was Kepler's first law. Planets orbit the Sun in ellipses, not circles, with the Sun at one focus of the ellipse. His second law described how a planet moves along that ellipse. A planet doesn't travel at a constant speed. It moves faster when it's closer to the Sun and slower when it's farther away. Specifically, a line drawn from the Sun to the planet sweeps out equal areas in equal times. This meant there was something about proximity to the Sun that affected speed, some relationship between distance and velocity that demanded explanation. And his third law, published in 1619, established a precise mathematical relationship between a planet's orbital period, how long it takes to complete one orbit, and its average distance from the Sun. The square of the period is proportional to the cube of the average distance. This law applied to every planet in the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn. All of them followed the same mathematical relationship with perfect precision. Kepler's three laws were empirical. He discovered them by fitting equations to Tycho's data. He did not explain why the planets obeyed these laws. He could not say what force or mechanism made a planet follow an ellipse, or what made it speed up near the Sun and slow down far from it. He described the motion as Galileo had described the motion of falling objects, with mathematics and without explanation. But take what Galileo and Kepler had done and lay it side by side. Galileo had shown that objects near the Earth's surface fall with uniform acceleration, that they all fall at the same rate regardless of weight, and that their motion follows precise mathematical laws. Kepler had shown that planets in the heavens follow precise mathematical laws too, elliptical orbits with predictable speeds, governed by relationships that could be expressed in equations. Aristotle's wall between earthly and heavenly physics was crumbling. The heavens were not perfect, eternal, unchanging realms of circular motion. They were messy, elliptical, variable. And the Earth was not a place of fundamentally different physics. Objects here and objects there both obeyed mathematical laws. Maybe, just maybe, they obeyed the same mathematical laws. But nobody had yet drawn that connection. Nobody had said, the force that pulls apples downward is the same force that keeps planets in their orbits. Nobody had unified terrestrial and celestial mechanics into a single framework. And nobody had explained why, what force or mechanism or principle made all of these mathematical descriptions true. That synthesis required a mind unlike any that had come before. And as it happened, such a mind was about to be born. On a farm in rural England, in the middle of a civil war, 3 months after his father's death, so premature and so small that the midwives did not expect him to survive the night. His name was Isaac Newton, and the mask he would place on gravity, the mask of force, would fit so perfectly that the world would wear it for 228 years without once suspecting there was anything underneath. To understand Newton, you first have to understand where he came from, because the distance between the farmhouse in Lincolnshire and the mathematical principles of natural philosophy is so vast that the journey itself is part of the story. Isaac Newton was born on Christmas Day, 1642, according to the calendar then in use in England, in the tiny village of Woolsthorpe in Lincolnshire. By the calendar used on the continent, it was January 4th, 1643, but Newton lived his whole life by the old reckoning, and there is something almost mythological about a Christmas Day birth for a man who would spend half his intellectual life studying biblical prophecy. He was dangerously premature. His mother, Hannah Ascough Newton, later told him that he was so small at birth he could have fit inside a quart mug. The midwives gave him no chance. His father, also named Isaac, had died 3 months earlier, an illiterate but prosperous farmer who left behind a stone farmhouse, a modest estate, and a widow with a baby she expected to bury before the week was out. But the baby lived. Stubbornly, improbably, he clung to life through the English winter, growing stronger with agonizing slowness while the country tore itself apart around him. England was in the grip of civil war, king against parliament, armies marching through the countryside, and the village of Woolsthorpe, remote and rural, stood apart from the chaos, a quiet backwater of muddy lanes and sheep pastures where most people never travelled more than a few miles from their birthplace. For 3 years, mother and son lived alone in the farmhouse, and then, when Isaac was 3, Hannah did something that would mark him for the rest of his life. She remarried. The man was Barnabas Smith, a wealthy rector 30 years her senior. Smith had money and status, but he came with a condition. He would not raise another man's child. Isaac would stay behind at Woolsthorpe with his grandmother, while his mother moved to her new husband's rectory, 1.5 miles down the road. Hannah agreed. She left her 3-year-old son and went to build a new life with a new husband. She would have 3 more children with Smith, children who lived with their mother while Isaac did not. The abandonment, for that is surely how a 3-year-old would experience it, scarred Newton deeply. Years later, as a teenager, he compiled a list of his sins in a notebook, a common Puritan practice, and among them he wrote, "Threatening my father and mother Smith to burn them and the house over them." The rage of a child replaced by a stepfather burned on for decades, perhaps for a lifetime. Newton grew up essentially alone. His grandmother was old and had little energy for a strange, withdrawn, fiercely intelligent boy. He had no playmates. He built elaborate mechanical devices, windmills and water clocks and sundials, marking his territory on the windowsills of the house where he felt unwanted, carvings that can still be seen there today. When Newton was 10, Barnabas Smith died, and his mother returned to Woolsthorpe with her 3 young children. Isaac was expected to share his home with half-siblings who had enjoyed the maternal affection he had been denied. The family dynamics were painful and complex, and Newton's emotional coldness, his inability to form close relationships, his obsessive need for control and recognition, all of it traces back with reasonable certainty to these years of abandonment and displacement. But someone had noticed the strange boy. Hannah's brother, William Ayscough, a clergyman with enough education to recognize intellectual gifts, insisted that Isaac was wasting himself on the farm. Despite Hannah's preference to keep Isaac at home tending sheep, William pushed for him to be sent to the grammar school in Grantham, 7 miles away. At 12, Isaac left Woolsthorpe for the King's School, where he boarded with the local apothecary, a man named William Clark. At first, Newton was unremarkable. He was quiet, withdrawn, poor at the competitive recitations that defined school life. But Clark's shop fascinated him. The jars of chemicals, the compounds, the equipment, the entire material world of substances and reactions drew him in, and he spent hours there, absorbing practical knowledge that no classroom could provide. The story goes that a bully kicked him in the stomach, and Newton, too small and weak to fight back, decided to beat the boy academically instead. He began studying with obsessive intensity, working by candlelight long after others had gone to sleep, and he rose from the bottom of his class to the top in a matter of months. Once he reached the top, he didn't stop. He had discovered that his mind was a weapon, and he had no intention of putting it down. When Isaac was 16, his mother pulled him out of school to manage the farm. She needed him. The experiment lasted several miserable months. Newton forgot to watch the sheep, which wandered into neighbours' crops. He brought books to the fields and sat reading while the livestock ran loose. He built a water wheel in a stream and watched it all day. He was, by any measure, the worst farmer in Lincolnshire. His schoolmaster, Henry Stokes, rode out to Woolsthorpe and begged Hannah to send the boy back to school. William Ayscough added his voice. Eventually, Hannah relented. Newton returned to Grantham, completed his education, and in June of 1661, at the age of 18, arrived at Trinity College, Cambridge, as a subcisar, the lowest rank of student, a servant to wealthier classmates in exchange for reduced fees. His mother, by now quite wealthy from 2 dead husbands' estates, gave him the bare minimum. So Newton, whose mind was already operating at a level that would have astonished any mathematician in Europe, spent his days cleaning the rooms and emptying the chamber pots of rich mediocrities who would never accomplish anything of note. The humiliation was profound, but it also fueled something. Every hour spent in servile labor was an hour stolen from study, and Newton began sleeping even less, working through the night by candlelight after his duties were done, driven by a determination to transcend his circumstances through sheer intellectual power. Cambridge in 1661 was still teaching the medieval Aristotelian curriculum. Students debated in Latin about the 4 elements, the natural places of things, the difference between celestial and terrestrial physics. Newton dutifully copied out the prescribed texts in his notebooks, the old framework that he would eventually destroy. But within months, he began discovering the new ideas that were sweeping through Europe, ideas that the official curriculum ignored. He found Descartes, who proposed that nature operated like a machine governed by mathematical laws. He found Gassendi, who had revived atomic theory. He found Galileo, whose mathematical description of motion was so far ahead of what Cambridge was teaching that it must have felt like discovering a secret. Newton taught himself mathematics with a speed that is hard to comprehend. He worked through Euclid, finding it too elementary to bother with. He moved on to Descartes' analytical geometry, to the algebraic methods of Viet and Oughtred, absorbing in months what would take most students years. By 1664, 3 years into his time at Cambridge, he had surpassed most of the established mathematicians in Europe. He had begun developing methods for calculating areas under curves and finding tangent lines, the foundations of what would become calculus. And he told no one. He filled notebooks with discoveries that would have caused a sensation if published, and he kept them entirely to himself. In the summer of 1665, the plague came to Cambridge. The bubonic plague, the Black Death, the disease that had killed 1/4 of Europe's population 3 centuries earlier and still returned in deadly waves. Cambridge closed, students scattered. Newton, 22 years old, returned to Woolsthorpe Manor with his books and his private notebooks. He would spend the next 18 months in near total isolation on his mother's farm. His mother was there, along with his half-siblings. The house was the same stone farmhouse where he'd spent his lonely childhood, with its thick walls and small windows, its cold rooms and narrow stairs. But now, instead of being an unwanted child with nothing to do, Newton was a young man with a mind on fire, finally granted the thing he needed most: uninterrupted time, absolute solitude. No lectures to attend, no professors to please, no social obligations to fulfill. Just silence and freedom and the contents of his own skull. And in that isolation, he would experience the most concentrated period of creative genius in the history of human thought. What happened at Woolsthorpe during those 18 months would later be called the Annus Mirabilis, the miracle year, though it actually stretched over a year and a half. Newton himself, looking back decades later, described it with characteristic understatement. In those days I was in the prime of my age for invention, and minded mathematics and philosophy more than at any time since. He was concealing the truth beneath dry words. What he accomplished during that period would have secured the eternal reputation of 3 or 4 different great scientists. He developed calculus into a complete mathematical system, giving it the name, the method of fluxions. He saw all changing quantities as flows generated by continuous motion. A curve was the path traced by a moving point. The velocity of that point at any instant, what he called its fluxion, corresponded to the slope of the tangent line. The area under the curve corresponded to the accumulated distance traveled. With this dynamic vision, he could solve any problem involving rates of change or accumulation. He discovered the binomial theorem. He found infinite series representations for trigonometric functions, for logarithms, for exponential functions. He could represent pi itself as an infinite series, calculable to any desired precision. And again, he told no one. He conducted his revolutionary experiments with light and color. Using a prism and a beam of sunlight admitted through a hole in his window shutter, he discovered that white light is not pure but composite, a mixture of all colors. Each color corresponds to a different degree of refraction. A prism doesn't create colors by modifying pure light. It separates colors that were already there. Newton tested this with a crucial experiment. He isolated a single color from the spectrum, passed it through a second prism, and found it emerged unchanged. Red stayed red. Blue stayed blue. Then he recombined all the colors with a lens and got white light again. 2,000 years of optical theory overturned by a man with a prism and a dark room. And Newton didn't stop at theory. He realized that the chromatic aberration that plagued refracting telescopes, those annoying colored fringes around the images of stars, was not a defect that could be fixed by grinding better lenses. It was a fundamental consequence of the nature of light itself. Different colors refract by different amounts. As long as you use lenses to focus light, you will get colored fringes. The solution, Newton saw, was to use mirrors instead of lenses. A curved mirror reflects all colors equally. No dispersion, no chromatic aberration, no colored fringes. In 1668, Newton built the first reflecting telescope, a tiny instrument just 6 inches long with a mirror about an inch across. By modern standards, it was primitive, but it produced sharper, cleaner images than refracting telescopes many times its size. When he presented it to the Royal Society in 1672, it caused a sensation. The design principle Newton invented is still used in virtually every major astronomical telescope in the world today, from the Hubble Space Telescope to the James Webb Space Telescope, to the giant ground-based observatories in Chile and Hawaii. Every time a telescope captures light from a distant galaxy using a curved mirror, it is using Newton's insight from a dark room in Woolsthorpe. And then there was gravity. The story of the apple is almost certainly true, though embellished by centuries of retelling. Newton himself told it to friends in his old age, and multiple independent sources record it with consistent details. He was sitting in the garden at Woolsthorpe, perhaps in the apple orchard behind the house, when he saw an apple fall from a tree. The sight was utterly commonplace. But something about that moment sparked a question in his prepared mind. Why did the apple fall straight down? Why toward the center of the earth, always without exception? How far did this tendency extend? The apple fell from a tree 20 feet up. Objects dropped from towers fell. But what about higher up? What about the clouds? What about the moon? The moon was clearly not falling to Earth. It stayed in its orbit year after year, century after century. And yet it was also not flying away. Something kept it in its curved path. What if that something was the same thing that pulled the apple? Think about what Newton was proposing. For 2,000 years, the physics of the heavens and the physics of the earth had been kept in separate categories. Aristotle had decreed it. The universities taught it. The church endorsed it. The sky was one kind of place, governed by one kind of physics. The ground was another. Newton was about to erase that boundary. What if, he wondered, the moon is constantly falling toward the earth, but moving sideways fast enough that it keeps missing? like a ball on a string swung in a circle, held in its circular path by the tension in the string. The moon falls and falls and falls, but the Earth curves away beneath it, and the fall never ends. An orbit is not the absence of falling. An orbit is falling, endlessly, with perfect aim that always misses. Newton already had the mathematics to test this. He knew the moon's distance from Earth, about 60 times the Earth's radius. He knew its orbital period, about 28 days. He could calculate how far the moon falls toward the Earth in each moment of its orbit, how much its path deviates from a straight line. And he could compare that with how far an apple falls in the same amount of time on the Earth's surface. If the same force governed both, and if that force decreased with distance according to some mathematical law, then the numbers should match. And Newton had reason to suspect a particular law. The inverse square law, where the force gets weaker as the square of the distance increases. Double the distance, the force drops to a quarter. Triple it, a ninth. This law has a certain geometric elegance, because it mirrors the way light from a candle spreads out, covering 4 times the area at twice the distance, 9 times the area at triple the distance. Kepler's third law, relating orbital periods to distances, also pointed toward an inverse square relationship, and so Newton ran the calculation. If the same inverse square law governed both, then the numbers should match. The moon, 60 times farther from Earth's center than the apple, should experience a gravitational pull that is 1/3600th as strong, 1/60 squared. And when Newton ran the calculation, the numbers came out close. Not perfect, about 10% off, but close enough to convince him that he was on to something profound. The 10% discrepancy troubled him. He was using the best available measurement of the Earth's radius, and that measurement was slightly wrong, about 10% too small. Newton didn't know this at the time. He knew only that his calculation was close but not exact, and for a man of his standards, close was not good enough. So he set the problem aside. He didn't abandon it, he simply shelved it, adding it to his growing stack of unpublished, half-finished revolutions. There were other problems demanding his attention, other questions pulling at him, and Newton moved between them with restless, obsessive energy, sleeping and eating irregularly, working alone in his room while his mother and half-siblings went about their lives in the farmhouse below, unable to comprehend what the strange young man upstairs was doing. But the apple had planted something. The idea that terrestrial gravity and celestial motion might be the same phenomenon, governed by the same mathematical law, that idea was lodged in Newton's mind, and it would not let go. It would take almost 20 years, better data, a furious rivalry, and the relentless prodding of a patient friend to bring it fully into the world. And when it finally emerged, it would change everything. The plague receded. Cambridge reopened. Newton returned to the university in 1667, carrying notebooks full of discoveries that no one had seen. He was elected a Fellow of Trinity College, which gave him a modest income and the freedom to continue his research. In 1669, at the age of 26, he was appointed Lucasian Professor of Mathematics, one of the most prestigious academic positions in England, a chair he would hold for the next 33 years. And for most of those years, he kept his greatest discoveries to himself. This is one of the strangest aspects of Newton's character. He had, by his late 20s, invented calculus, revolutionized optics, and laid the groundwork for a theory of universal gravitation. Any one of these achievements, published promptly, would have made him the most celebrated natural philosopher in Europe. Together, they would have caused an intellectual earthquake. But Newton published almost nothing. He shared his optical experiments reluctantly in a paper sent to the Royal Society in 1672, and the criticism it received, particularly from Robert Hooke, a brilliant and combative scientist who challenged Newton's conclusions, so infuriated and distressed him that he retreated even further into secrecy. Newton hated criticism. He hated it with a visceral, almost physical intensity that went far beyond normal scholarly defensiveness. Any challenge to his work felt like a personal attack, a threat to his status, a repetition of the childhood abandonment that had taught him to trust no one. His response was to withdraw, to refuse to publish, to guard his discoveries like a miser guards gold, sharing them only when forced to by circumstance or rivalry. And so the theory of gravity sat in his notebooks, unfinished and unpublished, for nearly 20 years. It might have stayed there forever if not for two things: a better measurement of the Earth's size and a conversation in a London coffee house in January of 1684. The measurement came from the French astronomer Jean Picard, who in 1669 had conducted a far more accurate survey of the Earth's circumference than any previously available. When Newton learned of Picard's result, probably around 1682, he went back to his old calculation, the one that had been 10% off at Woolsthorpe. He plugged in the new, more accurate value for the Earth's radius, and the numbers came out right. Perfectly right. The moon's motion matched the inverse square law of gravity exactly. The same force that pulled an apple toward the ground held the moon in its orbit. Newton reportedly became so agitated when he saw the result that he could not finish the calculation himself and had to ask a colleague to check it. The 10% discrepancy that had nagged him for 16 years vanished. The universe was telling him what he had suspected all along: one force, one law, governing everything from falling stones to orbiting planets. But he still didn't publish. The coffee house conversation happened in January of 1684, when three members of the Royal Society, Edmund Halley, Robert Hooke, and Christopher Wren, met to discuss a problem that had been nagging astronomers for years. Kepler's third law stated that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. What kind of force law would produce this relationship? If a force emanating from the Sun governed the planet's motions, how would that force have to vary with distance to produce Kepler's precise mathematical ratios? Hooke claimed he had solved it. The force would have to decrease with the square of the distance, an inverse square law. But when Wren offered a substantial book prize to anyone who could produce the actual mathematical proof, Hooke fell silent. He couldn't do it. Neither could Wren. The problem was too hard. In August of that year, Edmund Halley travelled to Cambridge to put the question to Newton. Halley was a remarkable man, an astronomer, mathematician and navigator with a warmth and diplomatic skill that Newton entirely lacked. He arrived at Trinity College and asked Newton directly, if the Sun attracted the planets with a force that decreased as the inverse square of the distance, what shape would the planetary orbits take? Newton answered immediately, ellipses. He had proved it years ago. Halley was stunned. He asked to see the proof. Newton rummaged through his papers, couldn't find it, but promised to redo the calculation and send it along. In November, he sent Halley a 9-page treatise called De Motu Corporum in Gyrum, on the motion of bodies in orbit. Halley read it and realized he was holding something extraordinary. He travelled back to Cambridge and urged Newton to expand the work into a full book. What happened next was one of the most intense periods of sustained intellectual effort in recorded history. Newton threw himself into the project with an obsessive, almost inhuman energy that alarmed everyone around him. For roughly 18 months, from late 1684 through the spring of 1687, he worked on the book that would become the Principia, the mathematical principles of natural philosophy. The process of writing the Principia was complicated by a bitter dispute with Robert Hooke, who claimed that he had given Newton the idea of the inverse square law. Hooke had indeed speculated about an inverse square law in correspondence with Newton, but he lacked the mathematical ability to prove anything. Newton was furious at the suggestion that he owed any part of his theory to Hooke, and at one point threatened to suppress the third volume of the Principia entirely, rather than give Hooke any credit. Halley, with extraordinary patience and diplomatic skill, managed to soothe Newton's rage and persuade him to complete the work. Without Halley's intervention, the Principia might never have been finished. His assistant at the time, Humphrey Newton, no relation, left a vivid account of this period. Newton rarely left his rooms. He ate almost nothing, often forgetting meals entirely. His food would be brought up and found untouched hours later. He slept at irregular intervals, sometimes working through 2 or 3 nights in a row. When he did walk to the dining hall, he would sometimes stop halfway, struck by a thought, and stand motionless in the courtyard for extended periods before turning around and going back to his desk. He spoke to almost no one. He was, in the language of a later century, in a state of flow so deep that the outside world had essentially ceased to exist for him. The Principia was published in July of 1687, funded largely by Edmund Halley, who paid for the printing out of his own pocket when the Royal Society ran short of funds. It was written in Latin, the language of scholarship, and it was dense, difficult, and deliberately obscure. Newton later admitted that he had made it intentionally hard to read, so that he would not be baited by little smatterers in mathematics. But for those who could follow it, the Principia was a revelation, and what it revealed was the second mask of gravity, the mask of force. Here is what Newton proposed. Every object in the universe, he said, attracts every other object with a force. The strength of that force is proportional to the product of their masses and inversely proportional to the square of the distance between them. Double the mass, double the force. Double the distance, the force drops to a quarter. Triple the distance, the force drops to a ninth. This was the law of universal gravitation, and the word universal is doing a lot of work in that phrase, because Newton was saying something that no one had ever said before. He was saying that the force that pulls an apple toward the ground is exactly, precisely, quantitatively the same force that holds the moon in orbit around the Earth, holds the Earth in orbit around the Sun, holds the moons of Jupiter in orbit around Jupiter, governs the tides, explains the precession of the equinoxes, and determines the trajectories of comets. One force, one law, everywhere, always. The wall between earthly and heavenly physics, the wall that Aristotle had built and that 2,000 years of scholarship had maintained, was gone. Not cracked, not damaged. Gone. The apple and the moon obeyed the same equation. The same mathematics that described a falling stone also described the orbit of Saturn. The universe was not divided into separate realms with separate rules. It was one single system, governed by one single law, and that law could be written in a single line of mathematics. And Newton didn't stop with the law of gravitation. The Principia also contained his 3 laws of motion, which together formed the foundation of what we now call classical mechanics. The first law stated that an object at rest stays at rest, and an object in motion stays in motion in a straight line at constant speed, unless acted on by an external force. This was the principle of inertia, the final demolition of Aristotle's claim that motion requires a constant push. Objects don't need to be pushed to keep moving, they need to be pushed to stop moving, or to change direction. The second law stated that force equals mass times acceleration. The force on an object is proportional to its mass and to the rate at which its velocity changes. This gave a precise, quantitative definition of what force means, something that had never existed before. The third law stated that for every action there is an equal and opposite reaction. When the Earth pulls on you, you pull on the Earth with exactly the same force. When a rocket expels gas downward, the gas pushes the rocket upward. Together, these 3 laws of motion plus the law of universal gravitation formed a complete system. Given the positions, velocities, and masses of any collection of objects, you could, in principle, predict their future positions for all time. The universe became, in the phrase that would echo through the following century, a clockwork. Wind it up, set it going, and the laws of motion determine everything that follows. Planets orbit, moons cycle. Comets swing through the inner solar system and arc back into the darkness. Tides rise and fall, apples drop from trees. All of it, every motion, every trajectory, every orbit, was a consequence of Newton's equations. Let me pause here, because the magnitude of what Newton had done deserves a moment to settle. For 23 centuries, since Aristotle, the universe had been divided into two kingdoms. Below the moon, the messy, imperfect, changing world of rocks and rivers and fire. Above the moon, the perfect, eternal, divine world of celestial spheres. Two sets of laws, two kinds of matter, two fundamentally different realms that had nothing to do with each other. Newton abolished that division with a single equation. The force that makes your coffee slide across the table when you bump it is the same force that holds Jupiter's moons in their orbits. The law that governs a child's ball bouncing on a sidewalk governs the comets that swing through the inner solar system from the frozen reaches beyond Neptune. There is no boundary. There is no wall between here and there, between mundane and celestial, between ordinary and sublime. Everything is connected. Everything obeys the same mathematics. That idea, the unity of nature, the notion that the entire universe, from dust motes to galaxies, operates under a single set of rules that a human mind can discover and write down in a few lines of mathematics. That idea is so familiar to us now that we forget how staggering it was. We grew up with it. We absorbed it from textbooks and documentaries and casual conversation. But in 1687, it was unprecedented. Nobody had ever demonstrated, mathematically and quantitatively, that the heavens and the earth are part of the same system. Newton was the first human being to show that the universe is one thing, governed by one set of laws, comprehensible by one mathematical framework. And the emotional weight of that demonstration, the sheer audacity of it, the feeling of a veil being lifted and revealing a cosmos of perfect mathematical order, stretching from the garden to the stars. That weight was felt immediately by everyone who could understand the Principia. The poet Alexander Pope captured it in a couplet that has endured for 3 centuries. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. The practical triumph of the Principia was immediate and overwhelming. Newton used his laws to explain the orbits of all the known planets. He explained the tides as a consequence of the gravitational pull of the moon and sun on the Earth's oceans. He explained the precession of the equinoxes, the slow wobble of the Earth's rotational axis, as a gravitational effect of the sun and moon on the Earth's equatorial bulge. He calculated the shape of the Earth itself, predicting that it would be slightly flattened at the poles and bulging at the equator, a prediction that was later confirmed by geodetic measurements. Edmund Halley used Newton's methods to calculate the orbit of a comet that had appeared in 1682 and to predict that it would return in approximately 76 years. When it did, right on schedule, in 1758, after both Halley and Newton were dead, it cemented Newton's reputation beyond any remaining doubt. The comet has been called Halley's Comet ever since. Over the next century, Newton's gravitational theory proved itself again and again. The discovery of Neptune in 1846 was perhaps its most spectacular triumph. Astronomers noticed that Uranus, discovered in 1781, was not following the orbit predicted by Newton's equations. It was being pulled slightly off course by something. 2 mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where an unknown planet would have to be to cause the observed deviations. They pointed their telescopes at the predicted spot, and there it was. Neptune, right where Newton's math said it should be. Think about what that means. A planet no one had ever seen, orbiting in the darkness billions of miles from Earth, discovered not through observation, but through mathematics. The force of gravity, expressed in Newton's equations, reached across the solar system and revealed a world that no human eye had glimpsed. The second mask fits so perfectly that it didn't just describe the known universe, it predicted parts of the universe that hadn't been discovered yet. And so, for 228 years, the question, "What is gravity?" had a clear, confident, spectacularly successful answer. Gravity is a force, an attractive force between all objects with mass. It acts instantaneously across any distance. It follows an inverse square law. It is described by a single, elegant equation. And that equation works. But there was something wrong, and Newton knew it. Here's the thing about Newton that people rarely discuss. The thing that separates him from almost every other triumphant scientist in history. He never believed his own answer. Oh, the mathematics, yes. The equations were correct, demonstrably, provably correct. They predicted planetary orbits, tidal patterns, comet trajectories, the shape of the Earth. The math was beyond question. But the underlying picture, the idea that gravity was a force reaching out through empty space, one object somehow grabbing another across millions of miles of vacuum with no physical connection, no medium, no mechanism. That idea troubled Newton deeply. In 1693, 6 years after the Principia was published, Newton wrote a letter to Richard Bentley, a theologian who had been using Newton's work in a series of lectures defending the existence of God. And in that letter, Newton made one of the most extraordinary admissions in the history of science. He wrote that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance, through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Read that again slowly, because it's remarkable. The man who discovered the law of universal gravitation is saying that the idea of gravity acting at a distance is an absurdity. He's saying that his own theory, the most successful theory in the history of science up to that point, describes something that he finds philosophically intolerable. Newton went on, "Gravity must be caused by an agent acting constantly according to certain laws. But whether this agent be material or immaterial, I have left to the consideration of my readers." In other words, the mathematics is correct, but I have no idea what the underlying mechanism is. Something makes gravity work. Something transmits the force across empty space. But I don't know what that something is, and I'm not going to pretend I do. This was Newton's famous declaration, hypotheses non fingo. I do not feign hypotheses. I will not speculate about the mechanism. The equations describe what gravity does, how it does it, why it does it, what invisible agent carries the force from the sun to the earth across 93 million miles of nothing. Those questions I leave unanswered. And this honesty, this willingness to draw a line between what he had demonstrated and what he had merely assumed, may have been Newton's greatest intellectual achievement, greater even than the equations themselves. Because the temptation to fill the gap with speculation must have been enormous. He could have proposed an ether, an invisible substance filling space, transmitting gravitational influence. Some of his contemporaries did exactly that. Descartes had imagined vortices of invisible matter swirling through space, pushing planets along their orbits. It was wrong, but it was at least a mechanism. Newton refused to offer one. He knew that his equations worked. He suspected that there was something deeper underneath. And he had the intellectual discipline to say, "I don't know what it is." The gap he identified, The gap between the mathematical description and the physical mechanism would sit there, unresolved, for 218 years. Physicists would use Newton's equations with spectacular success. They would discover new planets, calculate trajectories, predict eclipses, design ballistics. And every time they did so, they were implicitly using a model of gravity that their own founder had called absurd. Because here's the thing Newton couldn't resolve. His law of gravitation said that the force of gravity acts instantaneously. When the sun attracts the Earth, the pull is felt immediately, with no delay. If the sun were to suddenly vanish, the Earth would instantly stop feeling its gravitational pull, even though the sun is 8 light minutes away. Even though the light from the vanished sun would take 8 minutes to stop arriving. Gravity, in Newton's picture, is infinitely fast. It knows no speed limit. It reaches across the entire universe in 0 time. And that, in the early 20th century, would turn out to be a problem. Because someone was about to discover that nothing in the universe is infinitely fast. There is a speed limit. And it applies to everything, including, as it turns out, gravity. But Newton would not live to see his mask torn away. He died in 1727, at the age of 84, after spending his last 3 decades not in science but in running the Royal Mint, feuding bitterly with Leibniz over who had invented calculus, and writing more than 1 million words on biblical chronology and alchemy. He was buried in Westminster Abbey, among kings. His theory of gravity reigned unchallenged for more than 2 centuries. It worked so well, so precisely, so beautifully, that questioning it seemed not just unnecessary but almost blasphemous. Newton had given humanity a clockwork universe, and the clockwork ran perfectly. Almost perfectly. There was one small problem. One tiny, nagging discrepancy that refused to go away, no matter how carefully astronomers recalculated, no matter how many times they checked and rechecked and checked again. Mercury's orbit wasn't quite right. Mercury, the closest planet to the Sun, orbits in an ellipse, as Kepler had shown. But that ellipse doesn't stay fixed in space. It slowly rotates, a phenomenon called precession. The long axis of the ellipse drifts around the Sun, completing a full rotation over an enormously long period of time. Most of this precession could be explained by Newton's law of gravity, the gravitational pull of the other planets, Venus, Jupiter, all the rest, tugs on Mercury and causes its orbit to precess. Astronomers calculated how much precession all the other planets should cause, added it up, and compared the result with the observed precession. The numbers didn't match. Mercury's orbit was precessing more than Newton's equations predicted. The discrepancy was tiny, about 43 arcseconds per century, roughly 1/180th of a degree over 100 years. Absurdly small, but real, and persistent, and unexplained. Scientists tried everything. They proposed an undiscovered planet, which they named Vulcan, orbiting between Mercury and the Sun, whose gravitational pull might account for the extra precession. Astronomers searched for Vulcan during solar eclipses, looking for a tiny dark dot crossing the face of the Sun. They never found it. It didn't exist. The search for Vulcan consumed astronomers for decades. During solar eclipses, observers around the world scanned the face of the Sun for any sign of a small, dark planet crossing the solar disk. Several sightings were reported, and for a while the discovery of Vulcan seemed imminent. But none of the sightings held up. Different observers claimed to see Vulcan at different positions, and no consistent orbit could be calculated. The planet simply wasn't there. And yet Mercury's orbit kept precessing by those stubborn 43 extra arcseconds per century. They tried adjusting Newton's inverse square law, changing the exponent from exactly 2 to something very slightly different. That didn't work either, because any change to the exponent ruined the theory's beautiful agreement with all the other planetary orbits. For decades, the anomalous precession of Mercury sat there, like a splinter in the soul of classical physics, too small to seem important, too stubborn to go away, and waiting, patiently, for someone to understand what it was trying to say. That someone was a clerk in a Swiss patent office who liked to think about what would happen if you chased a beam of light. A man who had been rejected by every university he applied to, who couldn't get a job as a teaching assistant, who had been dismissed by the academic establishment as a nobody. A man who, like Newton before him, would do his most revolutionary work in isolation, far from the centers of institutional power, driven by nothing more than the questions that wouldn't let him sleep. His name was Albert Einstein, and the mask he would place on gravity would not just replace Newton's. It would reveal that Newton's mask, for all its brilliance, had been hiding something so strange, so counterintuitive, so utterly different from anything anyone had imagined that even Einstein himself would have trouble believing it at first. Albert Einstein was born on March 14, 1879, in Ulm, a small city in the kingdom of Württemberg in the German Empire. His father Hermann ran an electrochemical business with varying degrees of success. His mother Pauline was a musician with a strong personality and firm opinions. The family moved to Munich when Albert was an infant, and by most accounts he was a quiet, somewhat dreamy child who didn't speak until the age of 2 or 3. When he finally did, the story goes, he spoke in complete sentences, his first words reportedly a complaint that his milk was too hot. Whether that anecdote is perfectly true or partly embellished, it captures something real about Einstein's temperament. He observed before he spoke. He thought before he acted. He wanted to understand things thoroughly before opening his mouth. And when he did open his mouth, he tended to say things that disrupted conversations. When Einstein was about 5 years old, his father showed him a pocket compass. The experience left a mark that Einstein would remember for the rest of his life. The needle pointed the same direction no matter how he turned the case. Something invisible was acting on it. Something he couldn't see or touch or hear was reaching through the empty space between the compass and whatever was pulling the needle. That sense, the sense that behind visible things there are hidden structures, invisible architectures that govern how the world actually works, never left him. He was not, by the standards of his German schooling, a model student. He was brilliant in mathematics and physics, but stubbornly indifferent to subjects that bored him, and he had a questioning, skeptical temperament that did not endear him to the rigid, authoritarian teachers of late 19th century German schools. He eventually left the gymnasium in Munich without finishing, made his way to Switzerland, and applied to the Polytechnic in Zurich, one of the finest technical schools in Europe. He failed the entrance exam the first time. He was 16. He passed on his second attempt, enrolled, and graduated in 1900 with a diploma in physics and mathematics. And then he couldn't get a job. He applied to universities across Europe, rejected. He wrote to professors, offering to work as an assistant, ignored. For 2 years he scraped by with temporary teaching positions and private tutoring, a young physicist with big ideas and no institution willing to take him seriously. And then, through a friend's father, he got a position at the Swiss Patent Office in Bern, starting in 1902. Technical expert, 3rd class. His job was to evaluate patent applications, reading through proposals for inventions and assessing whether they were technically sound. Einstein later said the patent office was, in its own way, perfect. The work was engaging enough to keep his mind active, but not so demanding that it consumed all his intellectual energy. He could finish his patent evaluations by midday and spend the remaining hours thinking about physics. He had a small circle of friends in Bern, 3 guys who met in apartments to discuss philosophy, physics and mathematics over cheap food and strong coffee. They called themselves the Olympia Academy, which was a grand name for something that was basically a book club with equations. And it was during these years, this quiet period when nobody in the physics establishment paid him the slightest attention, that Einstein produced the most extraordinary burst of creative work since Newton's plague years at Woolsthorpe. In 1905, his so-called miracle year, he published 4 papers, each of which would have been enough to make a career. One explained the photoelectric effect, using the idea that light comes in discrete packets of energy, called quanta. That paper would eventually win him the Nobel Prize. One provided theoretical evidence for the existence of atoms by analyzing Brownian motion, the jittery random movement of pollen grains suspended in water. One introduced special relativity, and one gave the world E equals mc squared. But tonight, it's special relativity that matters most. Because that's where the story of time, being something other than absolute, really begins. And that's the first step toward the third mask of gravity. Here's the problem Einstein was grappling with. By the late 1800s, James Clerk Maxwell's equations of electromagnetism, published in the 1860s, had revealed something deeply strange. They predicted that light travels at a specific speed, about 186,000 miles per second, and that speed appeared in the equations as a constant. It didn't depend on anything. It wasn't relative to anything. It was just the speed of light, period. But that contradicted everything Newtonian physics said about how speeds work. If you're standing on a train platform and a train passes at 60 miles per hour, and someone on the train throws a ball forward at 20 miles per hour, you see the ball moving at 80 miles per hour. Speeds add up. That's Newtonian mechanics, and it's completely intuitive. So you'd expect the same thing with light. If you're moving toward a beam of light, shouldn't you measure it going faster? If you're moving away, shouldn't it seem slower? Maxwell's equations said no. The speed of light is the speed of light. It doesn't care how fast you're moving or in what direction. It's always the same number, for everyone, everywhere. Several physicists tried to resolve this. Hendrik Lorentz and George Fitzgerald independently proposed that objects physically contract in the direction of motion, that rulers literally get shorter when they move fast, which would explain why you always measure the same speed of light. Lorentz developed a set of mathematical transformations that described how measurements of length and time change between observers moving relative to each other. He came tantalizingly close to the full picture. But Einstein, in that 1905 paper, took the leap that Lorentz couldn't. He didn't try to explain away the constancy of the speed of light. He accepted it as a fundamental principle, a bedrock truth of the universe. And he asked, if the speed of light is the same for all observers, no matter how they're moving, what has to give? The answer was time. Time, Einstein showed, is not Newton's river flowing equitably for everyone. Time is personal. It depends on how you're moving. If you're moving fast relative to me, your clocks tick slower than mine. Not because your clocks are broken, not because of some mechanical effect, because time itself, the actual passage of moments, is slower for you. This is time dilation. And it isn't a philosophical musing. It's a measurable, testable, confirmed physical fact. Special relativity was revolutionary. It demolished the idea of absolute time that Newton had embedded in the foundations of physics. But it dealt only with objects moving at constant velocities, and it said nothing about gravity. Einstein knew, almost immediately, that he needed to go further. He needed to bring gravity into the picture. And the moment he started thinking about gravity, really thinking about it in that deep, patient, obsessive way of his, he had what he later called the happiest thought of his life. It came to him around 1907, while he was still at the patent office. The thought was this. Imagine a man falling off a roof. During the fall, for those brief seconds before impact, the man would feel weightless. A ball released from his hand would hover right there beside him. His keys, his wallet, a glass of water, everything would float. Because everything is falling together at the same rate. Relative to the falling man, nothing is accelerating. Nothing is moving. Einstein realized something profound in this. A person in free fall cannot tell the difference between falling in a gravitational field and floating in empty space, far from any planet or star, with no gravity at all. The experience is identical. There is no experiment you could perform inside a sealed, windowless room that would tell you which situation you're in. And it works the other way too. Imagine you're in a sealed room in deep space, far from any star, and someone attaches a rocket to the floor and accelerates you upward at 32 feet per second squared, the same acceleration you'd feel from Earth's gravity. You'd feel your feet pressed to the floor. You'd feel weight. You'd drop a ball and it would fall to the ground. Everything would behave exactly as if you were standing on the surface of the Earth. And no experiment you could perform inside that room would tell you whether you're being accelerated by a rocket or held in place by the gravity of a planet. This is the equivalence principle. Gravity and acceleration are, in a deep and fundamental sense, the same thing. Let me give you another way to feel this, because it's worth sitting with. You've been in an elevator. You felt that brief moment of lightness when the elevator starts going down, and that brief moment of heaviness when it starts going up. When the elevator accelerates downward, you feel lighter because the floor is, in a sense, partially falling away from under you, partially matching the free-fall trajectory that your body naturally wants to follow. When it accelerates upward, you feel heavier because the floor is pushing harder against your feet, adding its acceleration to the Earth's gravitational pull. Now, push that to the extreme. If the elevator cable snaps and the elevator falls freely, you feel weightless inside it. Zero gravity. And here's Einstein's insight: that zero gravity experience is not fake. You haven't turned off gravity. Gravity is still there. You're actually in the most natural state possible, following the path that space-time is offering you, without anything interfering. The sensation of weight that you feel when standing on solid ground, that is the artificial experience. The floor is stopping you from following your natural geodesic. Weight is the sensation of being interfered with. Think about that the next time you feel the solid floor under your feet. What you're feeling is not gravity pulling you down. What you're feeling is the ground pushing you up, preventing you from falling along the curved geometry of space-time. Gravity itself has no sensation. Free fall has no sensation. The only thing you feel is whatever prevents you from falling: the chair, the floor, the bed. Now, Einstein saw immediately what this implied. Special relativity had already shown that motion affects time. A moving clock ticks slower. Acceleration is a form of motion, changing motion. So if acceleration affects time and gravity is equivalent to acceleration, then gravity must affect time too. Gravity must slow time down. A clock on the surface of the Earth, deep in the gravitational field, should tick slower than an identical clock in orbit, where gravity is weaker. Time itself should flow at different rates, depending on where you are in a gravitational field. Einstein saw this in 1907. But working it out, actually building the mathematics to describe exactly how gravity warps time and space and the relationship between them, took him almost another decade. And those years, from roughly 1907 to 1915, were some of the most intellectually grueling years any scientist has ever endured. The difficulty was mathematical. Einstein needed to describe curved space-time, the idea that mass and energy actually bend the fabric of space and time, and the mathematical language for that is something called Riemannian geometry, or more specifically, tensor calculus. This was mathematics developed in the 19th century by Bernhard Riemann and others, originally as pure abstraction with no physical application in mind, and now Einstein needed it desperately, and he had to learn it almost from scratch. He was not, by his own admission, a naturally gifted mathematician. He was a spectacular physical thinker, He could see the physics, the underlying reality with an intuition that bordered on supernatural. But the math was hard for him. And the math he needed was extraordinarily hard. He turned to his old friend Marcel Grossmann, a mathematician he'd known since student days at the Polytechnic. The same Grossmann whose lecture notes Einstein had borrowed because he'd been skipping classes. Grossmann introduced Einstein to the tensor calculus of Ricci and Levi-Civita, to the whole apparatus of differential geometry. Together, between 1912 and 1913, they made significant progress. They published a joint paper, the Entwurf theory, that was a rough draft of general relativity. But it wasn't right. Einstein knew it wasn't right. The equations didn't have the full mathematical symmetry he was looking for. And so began what Einstein later described as some of the most agonizing years of his life. He would try one mathematical approach, follow it for months, convince himself it was wrong, abandon it, try another. He made errors. He published results he later had to retract. At one point, in 1913 and 1914, he actually talked himself out of the correct equations. He had them, or something very close to them, and he convinced himself they couldn't be right, and he walked away from them. Imagine that for a moment. Holding the answer in your hands and setting it down because you've persuaded yourself it must be flawed. Meanwhile, his personal life was falling apart. His marriage to Mileva Maric was disintegrating. He'd moved from Zurich to Berlin in 1914, partly for a prestigious position at the Prussian Academy of Sciences, partly because he'd begun a relationship with his cousin Elsa. Mileva stayed in Zurich with their two sons. The First World War broke out. Berlin was tense, resources were scarce, and many of his colleagues were swept up in nationalist fervor that Einstein, a committed pacifist, found repugnant. Through all of this, he kept working. He kept wrestling with the equations. Night after night, month after month, he ground through tensor calculus and differential geometry, searching for the right mathematical form, the equations that would describe how mass curves space-time and how space-time tells matter how to move. The physical idea was clear in his mind. He could see it, almost touch it. Mass bends space-time. Objects follow the curves. The mathematics has to express that relationship in a way that works regardless of what coordinate system you use, regardless of your point of view, regardless of whether you're standing on a planet or falling through space or spinning on a merry-go-round. The laws of physics must look the same to all observers. That was the principle of general covariance, and finding the equations that satisfied it was like solving a puzzle where the pieces kept changing shape. Einstein tried dozens of approaches. He would work for weeks on a particular mathematical formulation, filling pages with tensors and Christoffel symbols and Ricci curvatures, believing he was close, only to discover a flaw, an inconsistency, a failure to reproduce some known result, and he would have to start over. He described these years as a journey through a dark labyrinth, feeling his way along the walls, sometimes catching a glimpse of light ahead only to find it was a dead end. His letters from this period are revealing. He wrote to friends about his frustration, his exhaustion, his sense that the solution was tantalizingly close, but always just out of reach. To one correspondent he confessed that compared with this problem, the original relativity theory had been child's play. The difficulty wasn't just mathematical, it was conceptual. Einstein had to unlearn Newton. He had to abandon the idea of a gravitational force, the idea that had been the bedrock of physics for over 2 centuries, and replace it with something that had no precedent, no intuitive foundation, no familiar analogue. He was trying to describe a universe where the geometry of space and time is not a fixed backdrop, but a dynamic, evolving entity that responds to the matter and energy it contains. The stage is part of the play. The container is shaped by what it contains. And then, in the autumn of 1915, 2 things happened that pushed the story to its climax. First, Einstein learned that David Hilbert, one of the greatest mathematicians alive, was also working on gravitational field equations, approaching the same problem from a different direction, but with far superior mathematical tools. The possibility that someone else might publish the correct theory before him, after he'd spent 8 years of his life on it, drove Einstein to work at a feverish pace. Second, the equations finally began to cooperate. In November of 1915, Einstein gave a series of 4 lectures to the Prussian Academy, one each Thursday, each one refining and correcting the previous one. He was essentially working out the final form of the theory in real time, in public, week by week. On November 18th, he presented a calculation that sent his heart racing. He used his new equations to calculate the precession of Mercury's orbit, the tiny 43 arcsecond per century discrepancy that had baffled astronomers for decades, the splinter in the soul of Newtonian gravity. His equations gave exactly the right answer, 43 arcseconds per century, precisely. Einstein later told a friend that when he saw the result, he had heart palpitations. He said he felt something had snapped inside him. For 3 days he was beside himself with excitement, unable to concentrate on anything else. The equations worked. They explained something that Newton's theory simply could not. On November 25, 1915, Einstein presented the final, correct field equations of general relativity. And what those equations said was this: gravity is not a force. There is no invisible hand reaching across space and pulling objects together. There is no action at a distance. Newton's absurdity, the thing Newton himself had called intolerable, the notion of one body acting on another through a vacuum with no intermediary, that absurdity was dissolved. Because there is no force. There never was. What there is geometry. Mass and energy curve the fabric of space-time itself. The sun doesn't reach out and pull the Earth. The sun bends the space-time around it, and the Earth follows the curves. The Earth is moving along the straightest possible path through curved space-time, what mathematicians call a geodesic. In flat space-time, that path would be a straight line. But space-time near the sun isn't flat. It's curved. And the straightest path through curved space-time looks, from the outside, like an orbit. The classic analogy, imperfect but useful, is a bowling ball on a stretched rubber sheet. The ball creates a dip, a depression. Roll a marble nearby, and the marble curves toward the bowling ball, not because the bowling ball is pulling it, but because the surface it's rolling on is curved. The marble is just following the shape of the sheet. Space-time works something like that, though in 4 dimensions instead of 2, which is where the analogy starts to strain. And the analogy has a circularity problem. In the rubber sheet version, we're using gravity to make the bowling ball sink, which is the very thing we're trying to explain. So don't take it too literally. But the essential insight holds. There's a better way to think about it, and it involves time. Remember, space-time is not just space. It's space and time woven together. And it turns out that in most everyday situations, the time part of space-time curvature is far more important than the space part. When you stand on the surface of the Earth, space is barely curved at all. You wouldn't notice any difference in the geometry of your room compared to perfectly flat space. But time is measurably curved. Clocks at different heights tick at different rates. The flow of time changes with altitude. And it is this curvature in the time direction, this gradient in the rate of time, that accounts for most of what we experience as gravity. An object sitting on a table, apparently at rest, is actually moving through space-time. Not through space because it's sitting still, but through time. Everything moves through time. You're moving through time right now, at 1 second per second, heading into the future. The table is moving through time. The apple on the tree is moving through time. And when space-time is curved, as it is near the Earth, the direction through time is slightly tilted. It's tilted toward the center of mass, and that tilt is what we call gravity. When you release an apple, the apple follows the tilted direction of through time in curved space-time, and that direction points toward the Earth's center. The apple isn't being pulled, it's going straight, in the deepest geometric sense of straight, through a space-time that is bent. Objects in gravitational fields are not being pushed or pulled. They are following the natural contours of a curved landscape. They are going straight, in the deepest mathematical sense. It is the landscape itself that is bent. And here's the part that connects back to Einstein's happiest thought, the part about time. When space-time curves, it's not just space that bends, time bends too. Near a massive object, time runs slower, actually physically slower. A clock on the surface of the Earth ticks fewer times than an identical clock in orbit. A clock on the ground floor of a building ticks slightly slower than a clock on the top floor. This isn't a perceptual effect. It's not that time seems slower. Time itself, the actual passage of moments, the tick of atomic transitions, is slower in stronger gravitational fields. A second near a massive object contains fewer atomic oscillations than a second far from it. The deeper you are in a gravitational well, the slower your time flows. Newton's gravity was a force in space. Einstein's gravity is a shape of space-time. Newton's mask said, "Objects attract each other through empty space." Einstein tore that mask away and said, "There is no force, there is no empty space. There is only the curved geometry of the universe. And everything in it, planets, stars, light, you, follows the curves." The third mask was in place, and it fit even more perfectly than Newton's. But now the question was, could anyone prove it? Could anyone show that Einstein's curved space-time was not just a mathematical abstraction, but a description of actual physical reality? The answer would come from a most unlikely place, from the shadow of the moon, during a solar eclipse, on an island off the coast of Africa, 4 years into the bloodiest war in human history. Einstein's general theory of relativity made several testable predictions, and the most dramatic of them concerned the behavior of light near massive objects. If space-time is curved by mass, then light, which travels through space-time, must follow that curvature. A beam of light passing near a massive object like the sun should bend, its path deflected by the curved geometry of the space-time around it. Einstein calculated exactly how much the light from a distant star should bend as it passes close to the edge of the sun. About 1.75 arc-seconds, roughly twice the amount that Newtonian gravity would predict if you treated light as a particle with mass. The problem was that you can't normally see stars near the sun because the sun's glare washes them out. The only time you can see stars in the sky close to the sun's position is during a total solar eclipse, when the moon blocks the sun's disk and the sky goes dark for a few precious minutes. Arthur Eddington, a British astrophysicist, a Quaker and a pacifist who had spent much of the First World War arguing against military conscription, organized an expedition to test Einstein's prediction during the total solar eclipse of May 29, 1919. 2 teams were dispatched, one to the island of Principe off the west coast of Africa, where Eddington went himself, and another to Sobral in northern Brazil. They would photograph the stars near the sun during the eclipse and compare their apparent positions with their known positions when the sun was elsewhere in the sky. If the stars appeared displaced from their true positions by the amount Einstein predicted, it would mean that the sun's gravity was bending the starlight passing near it, curving the light's path through warped space-time. The conditions on Principe were difficult. It rained heavily on the morning of the eclipse, and clouds threatened to block the view entirely. Eddington later described the agonizing wait as the rain continued, the eclipse approaching minute by minute, the sky refusing to clear. Then, as the moon's shadow swept across the island and totality began, The clouds thinned just enough for the stars near the sun's obscured disk to appear. Eddington worked frantically, changing photographic plates, adjusting the telescope, trying to capture usable images in the few minutes of totality before the moon's shadow moved on. He managed to get several photographs. The team in Sobral had better weather and produced more usable plates, though ironically some of their best images came from a backup telescope that they had almost decided not to bring. When Eddington analyzed the results, the displacement of the stars matched Einstein's prediction. The light was bending by approximately 1.75 arcseconds, just as general relativity demanded. The Newtonian prediction, about half that amount, was ruled out. On November 6, 1919, the results were presented at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The announcement made headlines around the world. The Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein, virtually unknown to the general public the day before, became the most famous scientist on Earth overnight. Newspapers around the world carried his photograph. A young man with unruly hair and thoughtful eyes, the face that would become the most recognizable image of scientific genius in the 20th century. And the public responded not just with admiration, but with something closer to awe. Here was a theory that said space and time were curved, that gravity was geometry, that light bent around the sun. Most people couldn't follow the mathematics, but they could feel the strangeness of it. The sense that the universe was far more exotic than anyone had supposed, that the ground beneath their feet was not solid and fixed, but a flexible, malleable fabric shaped by the masses around it. Einstein became, in a very real sense, the first scientific celebrity of the modern era. The third mask had been tested, and it held. Space-time was genuinely curved. Light genuinely followed that curvature. Newton's picture of gravity as a force reaching across empty space was, after 228 years, officially superseded. But the eclipse test, dramatic as it was only the beginning. Over the following decades and into our own time, general relativity has been tested with ever-increasing precision, and it has passed every test. Let's talk about gravitational time dilation, because it's one of the strangest and most beautiful consequences of Einstein's theory, and because you can feel it, in a sense, right now. Einstein predicted in 1915 that time runs slower in stronger gravitational fields. A clock at sea level should tick slightly slower than a clock on a mountaintop, because sea level is deeper in the Earth's gravitational well, closer to the center of mass, where space-time is more curved. The difference is minuscule at Earth's surface, nanoseconds over extended periods, but it's real. For decades, no clock was precise enough to measure such tiny differences. But in 1959, Robert Pound and Glenn Rebka at Harvard conducted an experiment using gamma rays in a tower. They shot gamma rays from the bottom of a 74-foot tower to the top and measured the change in their frequency. General relativity predicted that the gamma rays should lose a tiny amount of energy climbing out of the gravitational well, shifting their frequencies slightly toward the red end of the spectrum. This is gravitational redshift, a direct consequence of gravitational time dilation. The photons were born in a region where time runs slower, so their oscillations appear stretched when observed from a region where time runs faster. Pound and Rebka's measurement agreed with Einstein's prediction to within 10%. Later refinements of the experiment reduced the disagreement to less than 1%. Time really does run at different speeds at different heights in a gravitational field. In 1971, Joseph Haffel and Richard Keating did something wonderfully simple and wonderfully audacious. They put 4 cesium atomic clocks on regular commercial airplanes, bought tickets, and flew them around the world. Eastward on one trip, westward on another. They sat in passenger seats with their clocks in the overhead bins, flying on Pan Am and TWA, alongside businessmen and tourists who had no idea that the most precise timepieces on the planet were traveling in the luggage racks above their heads. When the flying clocks came back, Haffel and Keating compared them with identical clocks that had stayed on the ground at the US Naval Observatory in Washington, D.C. The differences were tiny, measured in nanoseconds, but they were real and measurable. The eastward flying clocks had lost about 59 nanoseconds. The westward flying clocks had gained about 273 nanoseconds. And these numbers matched, within the experimental uncertainty, exactly what Einstein's theories predicted when you accounted for both special relativity, the time dilation due to the plane's velocity, and general relativity, the time dilation due to the difference in gravitational potential between cruising altitude and ground level. Both effects were real, both were measurable, and both matched the predictions. That was 1971. Since then, the experiments have become far more precise. Modern atomic clocks can detect gravitational time dilation between 2 points separated by as little as half an inch in height. A clock on your desk ticks at a measurably different rate than a clock on the floor. The difference is absurdly tiny, but it exists, and we can measure it. And here's where this becomes personal, where it stops being abstract physics and starts touching your everyday life. The GPS system, the network of satellites that lets your phone know where you are, relies on extraordinarily precise timing. Each GPS satellite carries an atomic clock, and your phone calculates its position by comparing the times at which signals from multiple satellites arrive. The speed of light is so fast that even tiny errors in timing translate into significant errors in position. Now, GPS satellites orbit at about 12,500 miles above the Earth's surface, where space-time is less curved than at ground level. Their atomic clocks run faster than clocks on the ground, by about 45 microseconds per day, due to gravitational time dilation. They also move at about 8,700 miles per hour, which causes their clocks to run slower by about 7 microseconds per day, due to special relativistic time dilation. The net effect is that GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. 38 microseconds per day doesn't sound like much, but light travels about 7 miles in 38 microseconds. If the GPS system didn't correct for relativistic time dilation, your position fix would drift by more than 7 miles per day. Within a week, the system would be useless. Every time you use your phone to navigate, every time a plane uses GPS to land, every time a delivery driver follows a map on a screen, Einstein's general theory of relativity is being applied, silently, automatically, invisibly, keeping the clocks synchronized across the curved space-time of the Earth's gravitational field. That is the third mask in action, every single day. But general relativity doesn't just correct GPS clocks and bend starlight. When you follow its equations to their most extreme conclusions, when you ask what happens when space-time is curved, not just a little, but enormously, catastrophically, you arrive at objects so strange that even Einstein didn't believe they could exist. You arrive at black holes. The idea emerged almost immediately after Einstein published his equations. In 1916, just months after the general theory of relativity appeared, a German physicist named Karl Schwarzschild, serving on the Eastern Front of World War I, found an exact mathematical solution to Einstein's field equations. He was calculating the curvature of space-time around a perfectly spherical, non-rotating mass, and his solution revealed something remarkable and disturbing. If you compressed a mass into a small enough volume, the curvature of space-time would become so extreme that nothing, not even light, could escape. There would be a boundary, a surface surrounding the compressed mass, beyond which the escape velocity exceeds the speed of light. Anything crossing that boundary, from the outside going in, could never come back out. Schwarzschild calculated the radius of this boundary. For an object with the mass of the Sun, it would be about 2 miles. For the Earth, about 1/3 of an inch. Compress either object below that radius, and it becomes, in the language that John Wheeler would coin decades later, a black hole. Schwarzschild sent his solution to Einstein from the trenches. He died a few months later, at the age of 42, from a disease contracted during his military service. Einstein was impressed by the mathematical elegance of the solution, but skeptical about its physical reality. Could nature actually produce such objects? Could a mass really be compressed to such extremes? He doubted it. For decades, many physicists shared his doubt, but the universe, as it often does, turned out to be stranger than physicists were willing to imagine. In the late 1930s, J. Robert Oppenheimer, the same man who would later lead the Manhattan Project, published a series of papers with his students, showing that when a sufficiently massive star exhausts its nuclear fuel, nothing can stop its gravitational collapse. The nuclear fusion that sustained the star, balancing gravity's inward pull with outward pressure, ceases. Gravity wins. The star collapses, and if it's massive enough, more than roughly 20 times the mass of the Sun, the collapse doesn't stop at any point. The matter falls inward. The curvature of space-time grows without limit, and a black hole forms. The implications are extraordinary. Inside the event horizon, the boundary that Schwarzschild calculated, all possible paths through space-time lead inward, toward the center. There is no direction you can move, no speed you can achieve, that will carry you back out. And at the very center, according to Einstein's equations, space-time curvature becomes infinite. Matter is compressed to infinite density. This mathematical point of infinite curvature is called a singularity, and it represents the place where Einstein's theory, beautiful and powerful as it is, breaks down. The equations give infinities, which in physics almost always means the theory has reached the boundary of its validity. To put the density of a singularity in perspective, consider this. The Earth, compressed to a black hole, would fit inside a marble with room to spare. The Sun, compressed to a black hole, would be a sphere about 4 miles across, small enough to sit comfortably inside a mid-sized city. And the supermassive black holes at the centers of galaxies, millions or billions of solar masses, have event horizons the size of our solar system. That is an object with the mass of 4 million suns, squeezed so tightly that nothing, not even light, not even information, escapes. And time near a black hole does something that sounds like it belongs in a dream. As you approach the event horizon, gravitational time dilation becomes more and more extreme. Your time slows down relative to a distant observer. If someone far away could watch you falling toward a black hole, they would see you moving slower and slower, your image stretching and reddening as the light climbing out of the gravitational well loses energy, shifting from visible light to infrared to radio waves to nothing. You would appear to freeze, fading, never quite reaching the horizon, hanging there for eternity at the edge. But from your own perspective, nothing unusual happens at the horizon. You cross it in seconds or minutes depending on the black hole's size, and you continue falling inward. The discrepancy between what you experience and what a distant observer sees is one of the most visceral demonstrations of gravitational time dilation. Your time and their time are so different that you literally cannot agree on when, or even whether, you crossed the boundary. For a supermassive black hole, the event horizon is so far from the center that tidal forces there are gentle. You could cross the event horizon without feeling anything unusual at all. You would only know you'd crossed it because, from that point on, every direction leads inward. Every possible path through space-time points toward the singularity. There is no outward direction anymore. Outward has ceased to exist. Most physicists believe that quantum effects, which general relativity doesn't include, become important near the singularity. Something must happen to prevent the truly infinite compression that the classical equations predict. But we don't have a quantum theory of gravity. We don't know what happens at the center of a black hole. And that uncertainty is not a minor footnote. It is a fundamental limitation of our understanding. The singularity is not just a place where the equations break down. It's a place where our ability to describe reality fails. It's a confession, written in the language of mathematics, that Einstein's beautiful theory, for all its power and precision and verified predictions, does not contain the final truth about gravity. Something deeper is needed. Something that works where Einstein's equations don't. Einstein's third mask, the mask of curved space-time, covers everything up to that point and covers it beautifully. But at the singularity, the mask tears, and behind it there is only a question mark. And there's something else about black holes, something almost philosophical, that I want you to sit with for a moment. Inside a black hole, beyond the event horizon, the singularity is not a place in space that you could somehow steer around or avoid. It is a moment in your future. The curvature of space-time inside the horizon is so extreme that the direction toward the singularity becomes a direction in time, not in space. You can no more avoid hitting the singularity than you can avoid reaching tomorrow. Your future, inside a black hole, points at the singularity with the same inevitability that your future outside points forward in time. The most extreme curvature of space-time produces a trap not in space but in time. Gravity, in its most extreme manifestation, doesn't just warp where you are, it warps when you are. Let that settle for a moment. Now, black holes were theoretical curiosities for decades. Elegant mathematical solutions, perhaps, but was there any evidence that they actually existed in the real universe? The answer came slowly, piece by piece, over the second half of the 20th century. X-ray telescopes detected intensely energetic radiation from compact objects in binary star systems, objects that seemed to have enormous mass concentrated in impossibly small volumes. Astronomers tracked stars near the center of our own galaxy, the Milky Way, and found them orbiting something invisible, something with a mass of about 4 million suns, packed into a region smaller than our solar system. In 2015, the detection of gravitational waves provided direct evidence of black hole mergers. Today, gravitational lensing is a standard tool in astronomy. When light from a distant galaxy passes near a massive object, a galaxy cluster between us and that distant galaxy, the light gets bent. Sometimes the light takes multiple paths around the massive object, and we see multiple images of the same distant galaxy, or the galaxy gets stretched into arcs and rings, called Einstein rings. By studying these lensed images, astronomers can map the distribution of mass in the lensing object, including dark matter, which we can't see directly, but which still curves space-time. Gravitational lensing has become one of our primary tools for studying the invisible scaffolding of the universe, the vast web of dark matter that holds galaxies and galaxy clusters together. And in 2019, the Event Horizon Telescope collaboration produced the first image of a black hole's shadow, the dark silhouette of the event horizon of M87 star, a supermassive black hole at the center of a galaxy 55 million light-years away. Black holes are real. Space-time really does curve so extremely that nothing escapes. And at the center of every one of them, Einstein's equations point to a singularity, a place where the mathematics produces infinities, where the theory confesses its own inadequacy, where the third mask, so spectacularly successful everywhere else, admits that it doesn't know what's underneath. But there's another place where the mask tears, another direction entirely from which the cracks are spreading. And to see it, we need to leave black holes behind for a moment and turn to something even more fundamental. We need to talk about gravitational waves, about detectors so sensitive they can measure a change in distance smaller than 1/10,000th the diameter of a proton. About a signal that arrived on Earth in September of 2015, a billion years after two black holes fell into each other in a galaxy far beyond anything our eyes can see. and about what that signal tells us about the nature of gravity itself. Einstein himself predicted gravitational waves back in 1916, just a year after publishing General Relativity. The logic was relatively straightforward, at least by Einstein's standards. If massive objects curve spacetime, and if those objects are accelerating, changing their motion, then the curvature should change too. And those changes in curvature should ripple outward through spacetime, like waves spreading across the surface of a pond when you drop a stone into it. Gravitational waves, ripples in the fabric of spacetime itself, traveling at the speed of light. But there was a problem, and the problem was size, or rather, smallness. Gravitational waves, even from extremely violent events, are phenomenally weak by the time they reach Earth. They stretch and squeeze space itself, alternately compressing distances in one direction and expanding them in another. But the amounts involved are almost inconceivably tiny. A gravitational wave from a cosmic event might change the distance between 2 points separated by a couple of miles by less than the diameter of a proton. For decades, most physicists thought gravitational waves could never be detected. The technology didn't exist. The precision required was beyond anything anyone could imagine building. Even Einstein went back and forth on whether gravitational waves were real physical phenomena or mathematical artifacts of his equations. At one point, in 1936, he actually submitted a paper arguing that they didn't exist, only to discover an error in his reasoning before the paper was published. But some physicists refused to give up. In the 1960s and 1970s, Joseph Weber at the University of Maryland built the first gravitational wave detectors, large aluminium cylinders that he hoped would vibrate when a gravitational wave passed through them. Weber claimed to have detected signals, but other researchers couldn't reproduce his results, and his claims were eventually discredited. Still, Weber's work inspired others to think seriously about detection, and by the 1980s, a new approach was taking shape. Instead of waiting for a gravitational wave to vibrate a solid object, you could use light itself as a measuring tool. The idea was to build a laser interferometer, split a laser beam into 2 perpendicular arms, bounce each beam off a mirror at the far end of its arm, and recombine them at the starting point. If the 2 arms are exactly the same length, the light waves cancel each other out perfectly when they recombine. But if a gravitational wave passes through, stretching one arm and compressing the other by even the tiniest amount, the light waves fall slightly out of sync, and you get a signal. This was the concept behind LIGO, the Laser Interferometer Gravitational Wave Observatory. It was proposed in the 1980s, primarily by Kip Thorne, Rainer Weiss, and Ronald Drever, and it took decades to design, fund, build, and refine. The project faced enormous skepticism. Critics argued that the required sensitivity was physically impossible, that the instruments would be overwhelmed by noise from earthquakes, traffic, ocean waves, thermal fluctuations, and 1,000 other sources. The laser would need to be extraordinarily stable, immune to the tiniest thermal fluctuations. The mirrors, 88 pounds of ultra-pure fused silica, would need to be the smoothest, most precisely shaped objects ever manufactured. The entire apparatus would need to be shielded from every conceivable vibration. Seismic waves from distant earthquakes, traffic on nearby highways, ocean waves pounding coastlines hundreds of miles away, even the microseismic hum of the Earth itself. The interferometer arms would need to be about 2.5 miles long. The mirrors would need to be suspended on elaborate vibration isolation systems. The laser beams would need to bounce back and forth hundreds of times to increase the effective path length. And the whole thing would need to measure changes in distance smaller than 1/10,000th the width of a proton. 2 LIGO detectors were built, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 1,800 miles. Having 2 detectors served as a check. A real gravitational wave would arrive at both detectors with a slight time delay determined by its direction, while local noise would appear in only one. After an initial observing run that detected nothing, LIGO underwent a major upgrade to advanced LIGO, with dramatically improved sensitivity. The upgraded detectors began their first observing run in September 2015. And then something happened that nobody expected. Not because it was physically impossible, but because of the timing. On September 14, 2015, just 2 days after the upgraded detectors had been switched on, still in their engineering test mode with no formal observing run underway, both detectors picked up a signal. It was loud, shockingly loud by the standards of gravitational wave detection. Clear and unmistakable, rising in frequency and amplitude over about 0.2 of a second before cutting off abruptly. When the researchers looked at the signal, they saw a pattern that matched theoretical predictions with eerie precision. The frequency was rising, chirping upward, which is exactly what you'd expect from two massive objects spiraling closer and closer together, orbiting faster and faster, emitting stronger and stronger gravitational waves until they finally merge. The signal corresponded to two black holes, each roughly 30 times the mass of the Sun, spiraling together and colliding about 1.3 billion years ago. The merger released energy equivalent to roughly 3 solar masses, converted entirely into gravitational waves. That's 3 times the mass of the Sun, turned into ripples in space-time, rippling outward in all directions at the speed of light. The signal was so clean, so perfect, that at first nobody believed it was real. The LILO team had a long-standing tradition of blind injections, fake signals secretly inserted into the data to test whether the analysis pipeline could detect them and whether the team could correctly identify them as fakes. Everyone assumed this was another test. But when no one came forward to claim the injection, and when months of painstaking analysis confirmed that the signal was genuine, they were forced to conclude something remarkable. 2 black holes had collided in a distant galaxy more than 1 billion years ago, before multicellular life existed on Earth, when our planet was stuck in what geologists call the boring billion, a long, stagnant period of evolutionary standstill. The gravitational waves from that collision had been traveling through the cosmos ever since, crossing vast tracts of empty space, passing through galaxy after galaxy, and they arrived at Earth just 2 days after humanity had finally built a machine sensitive enough to hear them. The timing was almost absurd in its perfection, as though the universe had been waiting. The signal, when converted to sound, is a chirp, a rising tone that sweeps upward in frequency and intensity and then abruptly stops. That chirp corresponds to the final moments of the in-spiral, the 2 black holes orbiting faster and faster, closer and closer, the gravitational waves growing stronger with each orbit, until the 2 event horizons touch and merge into one. The sudden silence after the chirp is the ringdown, the newly formed, larger black hole settling into its final shape, vibrating like a struck bell and then going still. The collision had released about 3 solar masses worth of energy as gravitational waves, more energy than all the stars in the observable universe were emitting as light at that moment. And it had traveled across 1.3 billion years of space-time to arrive at Earth and stretch LIGO's 2.5-mile arms by about 4/1000ths of a proton's width. On February 11, 2016, the LIGO collaboration announced the detection. In 2017, Weiss, Thorne and Barish, who had managed the project's construction, received the Nobel Prize in Physics. Since that first detection, LIGO and its European counterpart, Virgo, have detected dozens of gravitational wave events, merging black holes, merging neutron stars, and mixed mergers of a black hole swallowing a neutron star. In 2017, the detection of gravitational waves from merging neutron stars coincided with a burst of gamma rays observed by conventional telescopes, confirming beyond any remaining doubt that gravitational waves are real and that they travel at the speed of light, exactly as Einstein predicted. Now, why does this matter for the story of gravity's masks? Because gravitational waves tell us something crucial about the nature of gravity. They tell us that gravity is not instantaneous. It propagates. It moves through space at a finite speed, the speed of light. If the sun were to vanish right now, the gravitational effect would take 8 minutes to reach Earth, just like the light. Newton's picture, where gravity acts instantaneously across any distance, is wrong. Gravity has a speed limit, and that speed limit is the same as the speed limit for light and everything else. Gravity is a field, and it carries information, and that information travels at the speed of light. This also means that gravity carries energy. And the amounts of energy involved in gravitational wave events are staggering. The gravitational waves from that first black hole merger, the one detected in September of 2015, carried away roughly 3 solar masses worth of energy. Let that number sink in. 3 times the mass of the sun, converted entirely into gravitational radiation, ripples in the geometry of space-time, flung outward at the speed of light. For a brief fraction of a second during the merger, the gravitational wave luminosity, the rate at which energy was being radiated, exceeded the combined luminosity of every star in the observable universe. All the light from all the hundreds of billions of galaxies, each containing hundreds of billions of stars, was less than the gravitational energy pouring out of those 2 colliding black holes. Mass was converted into gravitational radiation and flung into the cosmos. Gravity is not just a passive geometric backdrop. It has its own energy. It can vibrate. It can propagate. It can carry information across 1 billion light-years, and that makes gravity behave in some fundamental respects like the other forces of nature. The electromagnetic field carries energy too, in the form of light, radio waves, X-rays. The strong and weak nuclear forces have their own field dynamics. All of those other forces have been successfully described using the framework of quantum mechanics, where energy comes in discrete packets, quanta, carried by specific particles. Photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. So here's the question that gravitational waves inevitably raise. If gravity is a field, and that field carries energy and propagates at the speed of light, just like the electromagnetic field, shouldn't gravity also have a quantum description? Shouldn't there be a quantum particle of gravity, a graviton, analogous to the photon? Shouldn't we be able to apply the same quantum rules to gravity that we've so successfully applied to every other fundamental interaction? That question brings us to the edge of the third mask, because when physicists try to answer it, when they try to combine general relativity with quantum mechanics, the mathematics explodes. Here's the problem, and let me lay it out slowly because it's genuinely one of the deepest puzzles in all of physics. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, is astonishingly successful. It explains how atoms work, why chemistry exists, how semiconductors function, why the sun shines. It has been tested to extraordinary precision, and it has never been found wrong. General relativity, the theory that describes the behavior of space-time at the largest scales, is also astonishingly successful. It explains black holes, gravitational lensing, the expansion of the universe, gravitational time dilation. It too has been tested to extraordinary precision, and it too has never been found wrong. But they are built on fundamentally incompatible assumptions. Quantum mechanics takes place on a fixed stage. Space-time is the backdrop, the arena, the container in which particles interact. It's flat, it's static, it's always there. Particles move through space-time. Fields vibrate in space-time. But space-time itself is not affected by what happens in it. It's like the stage in a theatre. The actors perform their drama, but the stage stays put. General relativity says the opposite. Space-time is not a fixed stage. It's a participant. It bends, it curves, it warps, it ripples. Mass tells space-time how to curve, and curved space-time tells mass how to move. Space-time is not the container of the physics. Space-time is the physics. When you try to apply quantum rules to gravity, you're trying to quantize space-time itself. You're trying to break the stage into tiny pieces, into quanta, into discrete packets, while the actors are still performing on it. And the mathematics that results is, to put it as plainly as possible, a disaster. The technical term is non-renormalizable. In quantum electrodynamics, the quantum theory of the electromagnetic force, you run into infinite quantities when you try to calculate certain things. But physicists discovered, in the 1940s and 50s, a procedure called renormalization that lets you systematically handle those infinities, absorb them into measured quantities, and extract finite, testable predictions. The procedure works beautifully for electromagnetism. It works for the strong force. It works for the weak force. It does not work for gravity. When you try to quantize gravity, the infinities multiply out of control. Every attempt to absorb them produces more infinities, and those infinities produce still more, in an endless cascade that no mathematical technique has been able to tame. Gravity, treated as a quantum field, excites itself. A gravitational field contains energy. Energy curves space-time. Curved space-time is more gravitational field. More gravitational field means more energy, which means more curvature, which means more field, and so on, without end. The two most successful theories in all of physics, quantum mechanics and general relativity, are fundamentally, stubbornly, apparently irreconcilably incompatible. And the place where they collide, the place where both theories should apply but neither one works, is wherever gravity gets very strong and distances get very small. At the center of a black hole, in the first instant after the Big Bang, at the scale of the Planck length, about 10 to the minus 35 meters, roughly a billionth of a trillionth of a trillionth of an inch, a scale so tiny that it makes a proton look like a continent. Einstein's third mask, the mask of curved spacetime, describes the universe beautifully at large scales. Quantum mechanics describes it beautifully at small scales. But at the place where they should meet, the mathematics collapses, and what we're left with is not an answer but a frontier. This is the edge of the fourth mask. And unlike the previous three, we cannot yet see what's underneath. But people are looking. They have been looking for decades, and some of their ideas are among the most extraordinary, most ambitious, most mind-bending proposals in the history of human thought. Let me tell you about three of them. The first is string theory. It proposes that the fundamental building blocks of reality are not point-like particles, but tiny, one-dimensional vibrating strings. Different vibrations of the same string produce different particles, just as different vibrations of a guitar string produce different musical notes. An electron is a string vibrating one way. A quark is the same string vibrating another way. A photon is yet another vibration. And a graviton, the hypothetical quantum particle of gravity, is yet another, a specific vibrational mode of the same fundamental object. String theory has a beautiful feature. It naturally includes gravity. Unlike other attempts to quantize gravity, string theory doesn't produce uncontrollable infinities. The extended nature of the string, the fact that it has length rather than being a dimensionless point, smooths out the mathematical divergences that plague other approaches. String theory is, as far as anyone can tell, a mathematically consistent theory that unifies quantum mechanics and gravity. But it comes with a price, a very strange price. For the mathematics to work, The strings need to vibrate not in the 3 dimensions of space and 1 of time that we experience, but in 10 or 11 dimensions. The extra dimensions, 6 or 7 of them, are not visible to us because they're curled up, compactified, folded in on themselves at scales so small that no experiment has ever detected them, and possibly no experiment ever could. This is either a profound insight into the hidden structure of reality, or an elaborate mathematical construction with no connection to the actual universe. String theory has been under development since the 1970s. It has produced extraordinary mathematical results. It has inspired enormous progress in pure mathematics, but it has not, as of now, made a single testable prediction that could distinguish it from other theories. Its critics call it unfalsifiable, a theory so flexible that it can accommodate any experimental result, which means it predicts none of them specifically. The extra dimensions are not just a technical inconvenience. They have physical consequences. In string theory, the way the extra dimensions are curled up, their precise geometric shape, determines which particles exist in our universe, what masses they have, and how they interact. The shape of the extra dimensions is, in a sense, the DNA of our universe. Different shapes produce different physics, different particles, different forces, even different numbers of spatial dimensions in the visible universe. And the problem is that there are an enormous number of possible shapes, perhaps 10 to the 500th power, each one producing a different version of physics. This landscape of possibilities makes it extraordinarily difficult to extract specific, testable predictions from string theory, because almost any experimental result could, in principle, be accommodated by choosing the right shape for the extra dimensions. Some physicists find this deeply troubling. Others see it as a sign that string theory describes not just our universe, but a vast multiverse of possible universes, each with its own version of physics, and that our universe happens to be one particular realization of the string landscape. Whether this is profound or merely unfalsifiable is one of the most heated debates in contemporary physics. The second approach is loop quantum gravity. Instead of adding new ingredients to the universe, like strings and extra dimensions, loop quantum gravity tries to quantize space-time directly, using the mathematical tools of general relativity itself. In this framework, space is not continuous. At the Planck scale, space is granular, made up of discrete, finite chunks, quanta of geometry, woven together in a network of intersecting loops. The fabric of space-time, which in general relativity is a smooth, continuous manifold, becomes, at the smallest scales, a kind of chainmail, a lattice, a foam. In loop quantum gravity, the singularity at the center of a black hole might not exist. The equations suggest that as matter is compressed to extreme densities, quantum effects create a repulsive pressure that prevents the collapse from reaching infinite density. The singularity is replaced by a bounce, a region of extreme but finite curvature. The tear in Einstein's mask, the infinity at the heart of a black hole, might be healed. In loop quantum gravity, area and volume come in discrete units, quanta. There is a smallest possible area and a smallest possible volume, determined by the Planck scale. Below that scale, the concepts of distance and area and volume lose their meaning entirely. Space, at the most fundamental level, is not a smooth continuum that can be divided without limit. It has a granular structure, like a fabric that looks smooth from a distance, but reveals individual threads when you examine it closely enough. And the threads of space-time, in this picture, are woven from loops of gravitational field. Loop quantum gravity has its own problems. It has difficulty reproducing the smooth, continuous space-time that we observe at everyday scales. Showing that a lattice of quantum geometry gives rise, at large scales, to the curved space-time of general relativity is a formidable mathematical challenge, and it has not yet been fully solved. And like string theory, loop quantum gravity has yet to make a definitive, experimentally testable prediction. The third idea is perhaps the most audacious of all, and it comes from a theoretical physicist named Lisa Randall. Randall is a professor at Harvard, a rock climber, and one of the most cited theoretical physicists of her generation. There's a story about her that captures something about the kind of person who works on these problems. She was climbing at Yosemite, scaling rock faces where the tension in a single rope is enough to overcome the gravitational pull of the entire planet. A daily demonstration of just how weak gravity is. Near the top of a climb, before she had secured her rope to the next anchor point, her grip failed. Gravity won, briefly, and she fell. She was airlifted out with a concussion, and during the enforced bed rest that followed, she had time to finish working through the theoretical implications of an idea she'd been developing with her colleague, Raman Sundram. In 1999, Randall and Sundram proposed something that sounds like it belongs in science fiction, but is in fact taken very seriously by the physics community. Randall and Sundram suggested that our entire universe might be a three-dimensional membrane, a brain, floating in a higher dimensional space. We are confined to our brain. We can only move in three spatial dimensions. We cannot reach into the extra dimensions, cannot see them, cannot directly detect them. And most of the forces of nature, electromagnetism, the strong force, the weak force, are similarly confined to our brain. But gravity, Randall proposed, is different. Gravity is not confined. It can leak into the extra dimensions. And this leaking is why gravity is so absurdly weak compared to the other forces. Think about what that means. The electromagnetic force is roughly 10 to the 36th power times stronger than gravity. That's a 1 followed by 36 zeros. The strong nuclear force is even stronger. The weakness of gravity compared to the other fundamental forces is one of the biggest unsolved problems in physics, and it even has a name: the hierarchy problem. Why is gravity so laughably feeble? Randall's answer? Because most of gravity isn't here. The gravity we experience is just the tiny fraction that leaks from another brain, another dimension, into our own three-dimensional world. On the gravitational brain, gravity is strong as the other forces. But the effects of that full-strength gravity decrease exponentially as they cross the gap between the brains, so that by the time they reach us, they're attenuated to a whisper. If that's true, then the weight you feel right now, the pull of your body against the mattress, is not the full strength of gravity. It's a faint echo, a shadow. The real gravity is elsewhere, in a dimension you will never touch, exerting its full power on a stage you will never see. This would also explain why gravitons are so hard to detect. In most quantum gravity theories, the graviton, if it exists, should be extraordinarily difficult to measure. But in Randall's framework, the difficulty has a specific physical explanation. Gravitons don't naturally belong on our brain. They're visitors from another dimension, and the probability that any given graviton will stray from the gravitational brain into our universe is vanishingly small. Let me give you a sense of how weak gravity really is, so you can feel the force of Randall's proposal. Pick up a paperclip with a refrigerator magnet. That tiny magnet, a few ounces of metal, is overpowering the gravitational pull of the entire Earth on that paperclip. The whole planet, 13,000 trillion pounds of rock and iron and magma pulling downward, defeated by a magnet you could lose between your couch cushions. Gravity is not just a little weaker than the other forces. It is staggeringly, almost absurdly weaker. And if you're a physicist, that asymmetry demands an explanation. Randall's idea provides one that is elegant, radical, and potentially testable. If extra dimensions exist, some of their effects might be detectable at very high energies, the kind of energies produced in particle accelerators like the Large Hadron Collider at CERN. Physicists have searched for signatures of extra dimensions in the LHC data, looking for particles that seem to vanish, their energy disappearing into a dimension that our detectors cannot reach. So far, no definitive evidence has appeared, but the search continues, and new, more powerful colliders are being planned that will probe even higher energies. There's another frontier of detection too. Astronomers believe that the Big Bang itself, or more precisely the period of rapid inflation that occurred in the first fraction of a second, should have produced a background of primordial gravitational waves, faint ripples still washing through the fabric of space-time after 13.8 billion years. Future detectors, including the European Space Agency's space-based LISA interferometer, may be sensitive enough to detect these ancient whispers. And the pattern of those primordial waves, their frequencies, their amplitudes, their polarization, could tell us something about the nature of gravity at the Planck scale, at the moment when quantum gravity reigned, and space-time itself may have been a boiling foam of fluctuating geometry. Now, is any of this true? Honestly, we don't know. String theory, loop quantum gravity, brain-world scenarios, these are hypotheses, mathematical frameworks, proposals. They are the work of some of the most brilliant minds in physics, and they represent our best attempts to peer under the third mask and see what lies beneath. But none of them has been confirmed by experiment. None of them has produced a prediction that has been tested and verified. And that's where we are tonight. We have lived through 4 masks. Aristotle's mask of natural places, which lasted 2,000 years. Newton's mask of force, which lasted 228. Einstein's mask of curved space-time, which has lasted 110 years so far, and which still works beautifully for everything we can currently measure. And somewhere underneath Einstein's mask, there is something else. A deeper truth about what gravity actually is. A truth that will resolve the conflict between quantum mechanics and general relativity. A truth that will explain what happens at the center of a black hole. A truth that will tell us whether space-time is smooth or granular, whether the universe has 3 spatial dimensions or 10, whether the gravity we feel is the full story or just a faint echo leaking in from elsewhere. We don't have that truth yet. We have candidates, ideas, mathematical structures that might or might not correspond to reality. We have the most sensitive detectors ever built, listening for gravitational whispers from the earliest moments of the universe. We have particle accelerators searching for hints of extra dimensions. We have telescopes mapping the curvature of space-time around black holes with increasing precision, looking for tiny deviations from Einstein's predictions that might point the way forward. And somewhere, perhaps in a quiet room, in a patent office or a university, or an apartment in a city you've never heard of, someone is thinking about gravity. Sitting with the problem the way Newton sat with it in a farmhouse during a plague, the way Einstein sat with it in a patent office during his lunch breaks. Turning it over, seeing something that no one else has seen, not yet ready to publish, not yet sure, but close. That's how the masks have always been torn away, by someone sitting alone with a question that wouldn't let go. And now, let's come back to you, because this story, all of it, every mask, every equation, every sleepless night in a farmhouse or a patent office, comes down to something very simple that is happening to you right now. You are lying in a gravitational field. Space-time around you is curved, very gently, by the mass of the Earth beneath you. And your body is following the contours of that curvature. Right now, in this moment, the mattress is pressing up against you, resisting your natural tendency to follow a geodesic through curved space-time. That resistance is what you feel as weight. Take the mattress away, take the floor away, take everything solid away, and you wouldn't fall. You'd be in free fall, which is to say you'd be following the straightest possible path through the geometry of the universe. You'd feel weightless. You'd feel nothing. Falling, it turns out, is the most natural thing you can do. Standing, lying, sitting. Those are the unnatural states. the states that require something to push against the geometry. So, in a very real sense, the mattress beneath you is not holding you up. It's preventing you from moving along the path that space-time is offering you. It's interrupting your fall. And the time passing for you right now, the gentle ticking of seconds in the darkness of your room, that time is slightly slower than the time passing for someone on the top floor of your building, or on a mountaintop, or aboard the International Space Station. The difference is absurdly small at the scale of a human life, nanoseconds over years, but it is real and it is measurable. Your time, the time of your heartbeat and your breathing and your drifting thoughts, is uniquely yours. It belongs to your specific location in the gravitational field of the Earth, in the gravitational field of the Sun, in the gravitational field of the galaxy. No one else in the universe, no matter how close they are to you, occupies exactly the same point in the geometry of space-time. No one else's time passes at exactly your rate. There's a wonderful detail from the history of science that I keep coming back to. When Newton wrote the Principia, he used geometric proofs instead of the calculus he had invented, because he thought geometry would be more convincing to his readers. When Einstein presented general relativity, he gave lectures on successive Thursdays, correcting himself each week, essentially discovering the final theory in public, in real time. When the LIGO team detected gravitational waves, the signal was so perfect that they spent months trying to prove it was fake before accepting it was real. Each of these moments has something in common. At the frontier of understanding, even the discoverers don't quite believe what they've found. The truth is stranger than what they expected, stranger than what they were looking for, stranger than what they thought the universe could be. And every time, the universe turned out to be right. 23 centuries of thinking about gravity, and this is where we've arrived. We started with Aristotle, who thought gravity was a longing, a desire of matter to return to its natural place, as though the stone missed the center of the earth the way a child misses home. That was beautiful, and it was wrong. We passed through Newton, who replaced the longing with a force, a precise, mathematical, universal force, reaching across space, binding every particle in the cosmos to every other particle. That was brilliant, and it was incomplete. We arrived at Einstein, who replaced the force with a shape, the shape of space-time itself, bent and curved by mass and energy, guiding everything along its contours. That was profound, and it may not be the final word. Because underneath Einstein's geometry, there is something we cannot yet see. Something that reconciles the quantum world with the curved world. Something that explains what happens when space-time curves so violently that the equations break. Something that might tell us whether the fabric of reality is woven from loops or vibrating strings, or brains floating in a higher dimensional void. The fourth mask is still dark. We can feel its edges, we can sense that it's there, but we cannot yet lift it. And maybe that's all right. Maybe the deepest truth about gravity is the one that Newton, of all people, understood most clearly. He knew that his equations worked. He knew they described the universe with precision that had never been achieved before. And he also knew that he did not understand what gravity actually is. He had the intellectual courage to say so. I do not feign hypotheses. I will not pretend to know what I do not know. Every great step forward in our understanding of gravity has been taken by someone who had that same courage. Someone who was willing to sit with a question that had no answer, to resist the temptation of a premature explanation, to keep looking even when the looking was exhausting and lonely, and produced nothing for months or years or decades. Aristotle offered a world where everything had a place and knew how to find it. Newton offered a world where invisible forces connected every atom to every star. Einstein offered a world where the stage itself was part of the performance, bending and flexing under the weight of the actors. Each of these pictures was richer, stranger, and more beautiful than the one before. The next picture, the one we haven't seen yet, will be stranger and more beautiful still. Of that, if the history teaches us anything at all, we can be quietly certain. But you don't need to worry about that tonight. The equations can wait. The questions can wait. The universe will keep curving, and the stars will keep falling along their geodesics, and the gravitational waves from colliding black holes will keep washing over the Earth, imperceptibly stretching and squeezing the space-time you're lying in. And none of it requires your attention right now. Right now, the only gravity that matters is the gentle pull holding you in place, the familiar weight of your own body, the soft, steady pressure of the mattress against your back. These are the things that are real right now, and they are enough. The first force that humans ever noticed, and the last one we will fully understand. Aristotle thought the stone was going home. In a way, he was right, though not in the way he imagined. The stone is following the geometry of the universe, tracing the curve that space-time offers, moving along the path of least resistance through a landscape shaped by everything that has mass and energy. In a very real sense, the stone is going where the universe tells it to go, going where it belongs, going home, not to the center of the Earth, but to wherever the geometry leads. And you, lying here in the dark, are doing the same, following the curves, moving through time along the path that the curvature of space-time lays out for you. You don't have to steer, you don't have to navigate, you just have to be, and the geometry does the rest. Maybe, after all these centuries, after all these masks, the deepest truth about gravity is the simplest one. It doesn't push, it doesn't pull, it just shapes the road, and everything, including you, is already on it. Let your breathing slow. Let the questions settle, like stones sinking through clear water, finding their own level. The universe is curving around you, very gently, and you are following its shape, and that is all you need to do. Good night.